Do we know if the bus has arrived or from ITTP? Well, I'm not worried about that. You want to check? No. It's just yesterday it arrived a bit late. But we can start. Yeah. Yeah, that's what happened yesterday with the bus. Right? It was a few minutes late.
Okay, I guess we should start. Yeah. My name is Paolo Carloni. I'm very happy to chair this morning session. I've been a PhD student of Michele some couple of years ago. A couple. And there's so many things have been said about Michele. For me, it's been life changer. I would like just to tell one episode that was right the first second so we met. So I told Michele, I'm here, I would like to learn your method. And of course, I'll do silicon, I think you're doing. I'm a biophysicist, so I said, okay. And then Michele said, there are so many people doing solid state physics here. Why don't you show me your protein? After a couple of minutes, I showed the protein. And Michele started to tell me things about this protein, been working on my PhD for a couple of years that I didn't think about it. I said, this is a good end of my PhD. That was something really remarkable. And I still enjoy very much learning from his method and collaborating with him to this date. Without further ado, I would like to introduce my client from Temple Universities, who's going to talk about Samuel Cray, and we look forward to your talk.
Thank you. Good morning, everyone. A pleasure to be here. I'm going to give a talk about the early days of computing. I came to create this talk because I have among my group of friends a lot of business people, self-made people, and asked me to actually give a talk. And so I put together a lot of slides. I've shuffled it down to about half the number I would normally use and try and see if I can keep it to half an hour. So the story begins in the 1930s, and a young man called Turing went to Cambridge to study mathematics, and he was a bright student. He finished in usual time, and he managed to get a scholarship to stay on and do research, which is pretty common in Cambridge. He stayed on at his own college, King's College. As I said, became a fellow. And then while he was in that intermediate position, he was a graduate, but not a graduate student. He took a course on logic taught by a mathematician called Max Newman. Max Newman was a refugee from Nazi Germany whose name was originally Neumann. He anglicized it. He was a rather brilliant logician, mathematician, and Turing was inspired by those lectures to think about a computing machine. And he went away and he wrote a paper which he went back and showed to Max Newman. And unbeknown to him, Max Newman was a serious mathematician, well-positioned. He was a fellow of the Royal Society. He was well-positioned with the British Mathematical Society, but he was also connected to Alonzo Church, who was a logician at Princeton, who had just created the Journal of Symbolic Logic. He was, in fact, the founding editor and had published papers on the same subject as Turing. Turing hadn't realized that he'd been scooped by Alonzo Church. And there's a beautiful comment I've highlighted in blue there, where Alonzo Church had sent a paper to Max Newman, the same field, and Newman had just received the paper from Turing, and then he says here, an off-print which you kindly sent me recently, in which you define calculable numbers and show that the decision problem is insoluble, had a rather painful effect on a young man, Alan Turing, who had just about to send in a paper for publication in which he had defined computable numbers for the same purpose. And so if you see here at the bottom, I've highlighted that Turing shows that they are equivalent and adds that to his paper. So what I find even more fascinating is that Turing then decides to go and do a PhD with Alonzo Church at Princeton, which of course, I think his fellowship enabled him to do that. He could go in the true Cambridge tradition, right? He could go where he wants, do what he wants. And, but that paper eventually came out, and you might be amused to know that there is an addendum to that paper, which most people don't cite when they cite the work, but I thought you might want to see what was wrong with the paper. So this is what was wrong with the paper. So those of you who are not mathematicians, I shouldn't worry about it, but the errors were pointed out by this guy, Bernays, a very eminent mathematician, Swiss mathematician. So while he was at Princeton, Turing came into contact with von Neumann, and von Neumann was keen for Turing to stay and be in the von Neumann circuit at the Institute of Advanced Studies, but Turing decided he wanted to go back to UK. So he went back to King's College. That was 1938. Already 39, the Second World War started, and Turing was assigned to Bletchley. This was not a random event. So many of the popular movies and plays and whatever have somehow melded in my mind Newman with Turing as one individual. In fact, Newman was much more important than Turing, in my view, reading these ancient documents. So it was Newman that brought Turing to Bletchley. Now, there's another factoid that I wasn't aware of when I was putting together this talk. It turns out that after the First World War, the French and the Poles were very suspicious of the Germans, and so they had a whole operation of mathematicians trying to decode the encrypted messages the German military were using. That was all, it's never mentioned where I grew up in England, but it turns out that this mathematician there that's honored now, all this, once Poland was invaded, then the Poles shared this with the Brits at Bletchley. So what was going on at Bletchley was not from the ground up. They already had a good start, and I'm not going to belabor that anymore. They were very successful. Now, it turns out one of the very first computers was in fact built by the British, called Colossus. And they made about a dozen of them during the Second World War. And the most important, does it work? The most important thing about, no, not working. It doesn't matter. Okay, let me go on. So the second individual I want to highlight is this young man, Claude Shannon. He was born in rural Michigan. He went to the University of Michigan when he was 16 years old. An ambitious young kid decided to do 2 degrees. He did mathematics and electrical engineering, and he finished in time, in 4 years. So when he was the age of typical high school graduate, he went to MIT to do his master's. Shannon was one of these nerdy geniuses, and he did do his PhD and master's degree at MIT, and I'll say a bit more about him. So Shannon is most famous for a publication he made in 1948. A lot of the work he did between when he joined Bell Labs and this 48 paper was classified, so it never got published till after the war. And he is the father of information theory, and this mathematical theory of communication. This one in the bottom. Oh, thank you, thank you. This mathematical theory here, when I looked to make this slide, there were 188,000 citations. So the only paper I know with more citations than that is PBE, with John Perdue, which is, I think, 220,000. But anyway, as I said, a lot of what Shannon did was secret, and I've highlighted there in the yellow part there. His theory is really how we communicate today. So let's go on. So what did he do for his master's thesis? He wrote the theory of how you lay down an electrical circuit. And I mean, you can read it faster than I can. So he developed a calculus for solving the equations for laying down a circuit. And he says the calculus is exactly analogous to the calculus of propositions used in symbolic logic. So people say this is the greatest master's thesis that's ever written. And I went to the MIT website, and you can download it. And so the total number of downloads of this thesis exceeds 100,000. So, and I was just curious, so I did download it, and there was immediately one very puzzling item. So they have redacted his signature on this one, but not his PhD thesis. I don't understand why. But the interesting thing here is the date is 1937, August. But when you look here, it's 1940. And then you look here, oh, this is when he's undergraduate. But when you look here, it was put in the library August 1940. Here's December 1940. So maybe he didn't pay the fee you were necessary to get your master's degree. Maybe he didn't actually file it. But being a typical nerdy guy, I don't think he cares one way or the other. But then I discovered that he got married in January 1940. So maybe the fact that he got married encouraged him to file for his master's degree and PhD. There's another possible interpretation, is he got a scholarship to go spend a year at the Institute of Advanced Studies, and maybe they wanted some proof that he actually had his degrees. If any of you don't know the story of Shannon, I encourage you to go look at this movie. It's about an hour and a half long. You can find it on YouTube. It is an incredible, it's an homage to him, written to celebrate the 100 years of his birth. It's a rather beautifully done movie. Well, he was an eccentric character at Bell Labs. He was known to work with his office door shut and not communicate with anybody. But if he went from A to B, he rode a unicycle along the corridor, juggling at the same time, different objects. So he was, but he solved the problem. If you want to take data from A to B in the presence of noise, he solved that problem, and that enables us all to communicate with our cell phones and other things. Not surprising he worried about that, because he was at Bell Labs, right, the telephone company. So he's most famous for some of these things that came out after that in publication. This one, for example, entropy of printed English, where a different letter is associated with it in entropy. the so-called Shannon entropy, which comes up now in the kinds of things many of us do. And then there are other papers, for instance, this one that was secret until 1949, the theory of secret systems and so on. So very, very nerdy, deep guy, worked on his own, didn't obviously collaborate. So fast forward 10 years, Second World War, Turing, when he got back, he was at Bletchley. And the British sent him to the United States because, remember, he had a PhD from Princeton, so he knew people. They sent him to spend 6 months traveling around to find out what the Americans were doing, because the Americans entered the war in 1942, but the war had started in 1939. So he was kind of a spy. And they told him to take nothing that can identify him as working on secret classified things. The man didn't take anything to identify himself and shows up at US immigration with no identification. So I don't know the story of how he managed to enter, but that's not written in the books. But anyway, he did spend 2 of the 6 months at Bell Labs, and rumor says every day he had tea with Shannon. It would have been wonderful to be the fly on the wall. What did these 2 nerds talk about? And there's a clue in the next slide that I'm going to show here. This is the fast forward 10 years, and Shannon was trying to put together a collection of articles on automata, and he wrote to Shannon wrote to Turing and said, can you contribute an article? And the wonders of the web, I was able to download the reply from Turing. And he says, thank you very much. Unfortunately, I'm not working in that field anymore. I'm working on mathematics and morphogenesis. Okay? And then he says, well, maybe you'll be interested in that, so I'll send you a copy of what I'm doing. But it shows the respect, because when that volume came out, Shannon actually wrote a chapter on the Turing machine. So it shows the mutual respect. I thought that was an interesting factoid to share. Of course, Turing committed suicide 1 year after that letter was written. Okay, Shannon became a celebrity because he constructed a mouse that could learn its way out of a maze. And the Bell Labs people made a movie of this, and he became a significant figure, although he hated this, right? He wanted to be left alone. But Vogue magazine had a cover of Audrey Hepburn, and inside there's an article, "The man machines may first talk to Dr. Shannon." So he was a bit of a celebrity. So the photographs we have of him really date from that Vogue interview. Okay, so what about computers? I don't have time to talk about all these computers, but several places were simultaneously working on computers for various reasons. Most of them were electromechanical. Some of them had valves. All this is before transistor. I could talk about all these. I don't have the time. I'm just going to focus on ENIAC that was built at the University of Pennsylvania. So it was commissioned by the military, and rumor says that it was used in part to help the design of the implosion device. The same story holds true for the machine that was built at Harvard by the Navy. Don't know if it's true. So this machine was built over a 3-year period by 2 engineers, Presper Eckert and John Mauchly, and the machine was in fact delivered to the military. This machine was designed to calculate trajectories of shells fired out of a cannon, basically. There's famous stories of there were no male mathematicians to hire, so they hired half a dozen female mathematicians. And when I read the obituary of Kay McNulty, she was the one that said, my working title was computer. So the first computer was a woman. Now, when I showed that slide in India, I got into deep trouble because they told me that when the Brits did the triangulation survey of India, the chief surveyor was called a computer. And he did such a great job, he was promoted, but he wasn't called supercomputer. But anyway, this is the first. So the people that used the machines and calculators were called computers. This machine was a giant thing, weighed 30 tons, 5 million hand-soldered pieces, not very practical, and it couldn't be programmed other than by rewiring it. And so these women computers literally had to wire a solution to a problem. So they were the programmers. So this is the first machine. So obviously the engineers that built that were interested in doing something a bit better. And von Neumann, who was into everything that was going on, he was the dominant mathematician around, the alpha male. He snooped around and ingratiated himself to these characters because he had an idea it would be much better if instead of doing all this rewiring, it could be done inside the machine. It seems, with my researchers, it's not clear to me whether Eckhart and Morkley already knew that themselves or whether von Neumann really brought that to the table. But in any case, von Neumann went and wrote a draft report of the next machine to be built and carefully distributed it without putting the names of Eckhart and Morkley, which, the way I look at it, seems to me scandalous these days. He would never have got away with it. But I guess he was such a powerful individual that he did. And by the way, he was a consultant to IBM. And so IBM knew everything that was going on. And so I'm not sure everything he did was honorable. Anyway, his report was widely distributed. But he also gave lectures on high-speed computing. And he was one to say, according to what I found, I've given a citation, von Neumann said, Turing's machine was simple and neat, but it didn't tell me how to build a computer, which is true, of course. However, it didn't stop von Neumann going around lecturing on Turing machines. Wonders of the web these days, I was able to download his lectures from 1945, lecture 3, The Logical Machine of Turing. So that's a bit of history. So what happened next was an explosion of interest in building machines. Eckhart and Morkley filed a patent for their machine. University of Pennsylvania wanted them to sign over all the royalties to the university. They refused. They both resigned their position, and they made their own company. And that company was the, is it on there somewhere? It was called the Electronic Computer Company or something like that. And then it also changed again. So remember that this second generation machine was already conceived and widely distributed. And they managed, Eckhart and Morkley managed to sell it to the ballistics lab, and a version was built and delivered in 1949. Now, Turing, after the war, was recruited and hired at the National Physical Laboratory, where he was put in charge of designing a computer, which he did, of a similar type. But they decided it was too complicated to build, and they just built a prototype. And this was actually marketed at some point. A second copy of the EDVAC was built and assembled, working in 1952. Here, canonical people here you'll recognize. So von Neumann was sufficiently influential and powerful that he got the second version of that machine in Princeton. Now, Turing, when he left National Physical Laboratory, Max Newman, who was his professor back at Cambridge, was in charge of this project at the University of Manchester. Newman left Cambridge and went to the University of Manchester and was connected with the development of the first machine here built in the UK. And he brought Turing to Manchester. That's how he got there. And it says here he wrote a programming manual for this first machine. So this was a machine that was then commercialized in the UK that came out about the same time. So there was a lot going on. Now, also in the US, this is a very important development. All the branches of the army had code breaking going on, and they needed computers. And the Navy didn't want to lose this, so it did a startup, Engineering Research Associates, and Engineering Research Associates built computers. And this is, in fact, where UNIVAC came from. And they built machines and delivered them as well. And they got to a point where the Congress or politicians didn't like the fact that the Navy had its own company to build it computers, so they had to divest themselves of that. So that led to some changes. So Engineering Research Associates was actually where Seymour Cray started his life. I've got it here. He fought in the Second World War. He fought in the Battle of the Bulge to get into Germany, and then he was transferred to the Pacific to do code breaking. And then he went, after the war, he went to university. He studied electrical engineering. He graduated, and then he took a master's in mathematics. And while he was doing his master's in mathematics, he joined ERA and was associated with the design and building of the UNIVAC 1103. And here's a picture of UNIVAC 1103. So he was very much involved in that. So here's the story of UNIVAC, but there's an interesting story about this, which I'll jump ahead to. So these first computers were built in Philadelphia, and I only discovered that printing this. And you can go and see, the building is still there. They were actually built in Philadelphia. I never knew that. As I said, Cray comes into the picture here with the UNIVAC, and this year is the 100th anniversary of his birth, and it's actually the 50th anniversary of him announcing the Cray 1. So let me go through that. So that's here. So he joined the ERA. Just to say a little bit more about UNIVAC, because it was actually sold to do the US Census, the first one, which is significant, 1951. It was a real machine, it worked, and it went through various editions. And the 1108 was a machine I used in the early 70s at the University of Paris, working with Jean-Pierre Hansen and others. But this is the story I wanted to get across. It's a really interesting one. There were two companies in the US doing computers. There was Eckhart Maughley Company, and there was ERA. And it turned out that when General Groves finished his term in doing the bomb and controlling, he seemed to be good at getting academics to do useful things. He joined Remington Rand to be in charge of the advanced research. And the first thing he did was buy the two companies in the US that were making computers. It so happened that the Maughley Company lost its contracts to build computers. Can you imagine? They lost it because they had communist engineers. Miracle of miracles. When Groves bought it, suddenly they got all their contracts. I put up there, all's fair in love and war. So Remington Rand accumulated those two companies that became UNIVAC. Now there was the Maniac machine. I won't spend a lot of time on that because most people kind of imagine this is the first machine, but it's really the same machine that was installed already in Princeton and elsewhere. So we have the story of Metropolis. But let's go on. IBM wasn't quiet. IBM was a business company, right? And so in the same era, and they knew everything because of von Neumann, they knew everything going on in the other companies. IBM had a 701 and a 704, and these were the early machines that really dominated the market, not the other ones. Don't have time to say much about. So IBM decided it would build a supercomputer, and it did. It was called the 7030, or Stretch it was called. It was delivered to Los Alamos. It was the fastest machine in the world for a while, until the Control Data Corporation released its 6600 here. But it never met the performance goals. It was delivered, they used it for a few years, but it really wasn't that great. So then Seymour Cray, I mentioned he joined CDC, and he was designer of this 1604, designed the 3600 and the 6600. So one shout out I want to give, he was obsessed with industrial design, and I was able to find on the web an original designer of what this machine should look like. So he really believed that if you were going to try and convince somebody to spend millions of dollars on a computer, it better look beautiful. So this had to be covered with black glass, and you see this is from the 60s, and he succeeded. He built a beautiful machine. So what I wanted to do here is just point out to Michele, if you read carefully the 64 paper of Anise, he used both the CDC 3600 and the IBM 704. He used both of those. And they were pretty much equivalent. I'm going to go fast forward here. The 3600 was a machine I used in the early 70s at the Atomic Energy of Canada Research Labs. IBM did build a great machine, the 360. We had it in the lab where I was employed, and I used it when I visited IBM. But the best machine of that era was the 6600, designed by Seymour Cray. There was an interesting thing happened here, and a bit of nasty work here. So CEO of IBM made this quote. Last week, Control Data announced the 6600. In the lab developing this system, there were 34 people, including the janitor, 14 engineers, and 4 programmers. I failed to understand how we lost leadership position when we have hundreds and hundreds of people working. So they started a new project. They put 200 people in California to correct this situation. And there was a lawsuit because, as I said, all's fair in love and war. IBM announced a new Model 90, which didn't exist. And people knew it didn't exist, and there were lawsuits, and IBM had to pay CDC $600 million. So when you compete in the real world, it can get tough. So here, I want to show this because, again, Seymour Cray believed his machine should look beautiful. So this was finished with walnut and sapphire blue glass, just to make it look attractive, to persuade you that millions of dollars were well spent. So I used the IBM machines in 1970, don't have time for that. I used the UNIVAC I mentioned, don't have time for that. So Cray had this vision to build the ultimate supercomputer, but CDC wouldn't bankroll it. So he left and created Cray Research in 1972. He raised his own money, and he built the Cray 1. Announced it in 75, delivered in 76 to Los Alamos. Now, those of you that heard my talk after dinner would remember I said the 1970s were different. He worked all alone in designing this. It took a year to build the machine, actually assemble it. And here's a picture of him standing in front of the first Cray 1. You see the outfit he's wearing and see the colors of the machine. This, I need a couple more minutes, right? So here's the facts about this machine. So first of all, it was described as a $9 million love seat because of the thing around the bottom. It took a year to build, 60 miles of wiring inside. That's why it took a long time to build. But it was the fastest machine in the world. Then there was a succession of other machines. I won't discuss them in detail, except to say, as Michele pointed out in his remarks yesterday, he said he was able to do his thing because Chineka had acquired an XMP. So this is incredible that they had, right? It's absolutely incredible. And so, and Chineka updated to the many processor Crays when they came out. But that was not designed by Seymour Cray, the last one. In my group, Michiel got to use the Cyber 205, which was a CDC machine. Don't have time. But a couple of pictures to just show you again how they like these machines to look beautiful. So this is the computer center at CERN with its Cray computers. So they look attractive, and there were others that were built. I don't have time to go into that, so I'll keep going. The last machine that actually he built and sold was called the 90. I think this was a poke in the eye for IBM that claimed they'd built a machine called the 90. And it wasn't very popular. It sold only 2 or 3 copies. And then he started another company to try and build the Cray 3. And that coincided with the end of the Cold War and no demand for supercomputers. The market disappeared. It went bankrupt. And he died in a car crash a year later. I couldn't see any indication that that was a suicide. A couple of quotes, and I'm going to stop. Read the left panel. When asked what design tools he used, Seymour Cray said he liked number 3 pencils and paper turned on the back, writing on the back so the lines were less visible. And then he was told, Apple just bought a Cray to help design the Mac. He replied, well, I just bought a Mac to design the Cray. So anyway, he was a remarkable man, incredibly influential, and I think that's pretty well the end for me. Huge newspaper headlines when he died. They just go on and on and on. The company continues. The one that he left to build the Cray 1 is still there, went to massively parallel, and Hewlett-Packard eventually became the owner of that. And this is my last slide. If you look at the list, the latest list of the top 500, the name Cray is on 4 of the top 5. And so Cray's name inextricably linked with supercomputers. And that's it. I'm done.
Thank you very much, Mark. It's time for a short question, comment from the audience. I have one. I'm very curious what happens to the German first computer.
Yes. So the SUSE.
Yeah.
So the German computer was there, of course, unknown to US and UK, I mean, because it was done in the Nazi era. It was, in fact, a working machine. And the same mathematician that criticized Turing's work, Bernays, is the guy that brought the SUSE machine to EPFL in Switzerland in the 1950s. And I think it ran for about 10 years. The great thing about SUSE's machine was it was programmable. These other electromechanical were, yeah. So he developed his own language for the machine. Really a phenomenal person. I said I have lots of slides on that, but no time.
Thanks a lot. We thank Mike again for his nice talk. And we move to the next speaker.
Good morning, everyone. I'm Haiyang Liu, come from Northwestern Polytechnic University. It's a great pleasure and honor to be here to attend this wonderful conference. Thanks for the organizers and also celebrate Michael's birthday with you. Today, I would like to talk about phase transition in materials and how to understand it. Actually, my journey to do phase transition can be tracked back to 12 years ago. At that time, I was still a joint PhD student at MIT Moscow in a group led by Professor Artem Ganov. And on December the 1st, I remember that they were quite well. Atom organized a conference, and in that conference, Michaela, okay, this gentleman is Michaela, and he gave a talk, molecular dynamic simulation of crystal growth. I cannot remember all the details, but I'm fascinated by those elegant element molecular moves and how they arrange to the Ura crystals. And eventually, was extremely lucky that I joined Michaela's group in 2016. And a special thing I want to mention here is that for every new year, Michaela will organize a special party for us who cannot celebrate New Year with families. Look at here, Barak and Zadia. And Jenny cooked very delicious food. And also, we enjoyed Motai. And well, Motai is the best liquor in China. Please don't Google the price, otherwise you will be jealous of me. And so let's back to crystallization, nucleation. We are all very familiar with these processes, and how to simulate at atomic scale is quite challenging, I would say. So from a disordered state to ordered. Now, when we mention about order, the first thing came to our mind is crystal, and actually there are many ways to understand crystals, and the most powerful way is X-ray diffraction. In fact, 99% of the experimental identified structures are by X-ray. So at that time, my colleagues, Michael and Vanessa, are playing with VS and structure factor at some specialty we think about. Why don't we use structure factor directly as a collector variable, and it turns out to be super powerful. And for instance, crystallization of silicon, crystallizing of perovskite structure, extremely complex structure. And also, from that point, I started to doing a lot of crystallization problems, and like crystallization of gallium. Actually, this work is from Xingao almost 40 years ago, and fascinating work, and inspired us a lot. And in the summer of 2017, Wanda visited the group, and Michaela said to Wanda, Haiyang can crystallize everything. And I'm so pleased and felt, oh my God. So I chatted with Isaac, my dear friend and colleague, that Michaela said, I can crystallize everything. And Isaac said, okay, how about water? And until yesterday, I realized that I worked on water is because of my destiny. Haiyang in Chinese means ocean. So bunches of water, so I started working water freezing. We all know water freezing is an extremely complicated process, and the structure of water, as many of you have mentioned, is still not fully understood. And how does ice form is not easy to understand. And there's another problem actually related to crystallization of ice is because it can be turned into hexagonal ice or cube ice. We do not want to prejudge or bias the simulation, but if you look at the structure, the single layer is always a honeycomb. So we proposed, why don't we use two-dimensional structure factor, replace the Shane function with Bessel function, and it turns out extremely well. And so, if we check the history, actually, one remarkable work is by Omeni group, and they said ice is born in a region with bounties of long-lived hydrogen bonds, and many other following works have give some very valuable results. I would like to summarize in my opinion that those key things. Ice is born in a region with long-lived hydrogen bonds, high hydrohydrality, low mobility, and low density. But because the network is so complex, the way how it reconstruct, I would say is quite difficult to capture. So we have used the machine learning potential developed by Lin Feng, etc., and run forward flash sampling, and eventually with thousands of independent MD simulations, we got this nucleation process for 36 microseconds from scratch. And this is how ice is born. And this is ice baby, and you can see that it's surrounded by beautiful structure, especially those green sided region is the high mobile region. And if you look at here, actually, no matter the growth or the shrink of the nucleus is always connected with the high mobile region. Actually, ice is not born in the low mobile region, but in a coexisting high mobile and low mobile region. And the high mobile region plays a role to drive the hydrogen bond network reconstruction. The low mobile region is protect the nucleus from melting and also from growing. And if we go to more details, we can see this region actually is full of molecules that we named as imperfect coordinate molecules. They have quite strong correlation in structural heterogeneity in the supercooled water induces these processes and determines the underlying mechanism. And so, mentioning about molecules and their coordinations, we defined that for perfect coordinate molecules, two donating and two accepting hydrogen bonds, and the others as imperfect coordinated molecules. And if we check the hydrogen bond network, the whole process is by the IC status generation, transfer, and annihilation. And I want to summarize that it is imperfect water molecule that makes ice perfect. Because of those bounties of simulations, and we can directly estimate the nucleation rate no matter from FFS or umbrella sampling, and this is the point we have estimated. The yellow sided region is experimental value, and those are previous simulations, usually several orders degree under estimate compared to experiment. And actually during this, all those ice nuclear simulation, occasionally we simulate a cell with a super mini cell, let's say 64 atoms, and you usually can crystallize automatically. And this really inspired us. Why don't we explore the whole ice landscape? We know it's a very complex phase diagram, and with 20 in nature or experimental identified ice phases. So we combined the machine learning potential with crystal structure prediction method, USPEX, developed by Atom, and then we ran the simulation at ambient pressure. Actually, the idea is not us, and I think Michaela and some of you already used this idea quite many years ago, and I would say like a catalysis. At 0 Kelvin, the structure is like, if you want to reconstruct the hydrogen bond network, not easy, but at ambient pressure with a small cell, you can automatically get an extremely composite ice phase, like ice fall. And so we have sampled over 130 sovereign ice structures, beautiful and elegant shapes. And with all those structures, we have identified 34 new ice candidates that is highly likely to be synthesized, I would say. there is one special phase, we name it as ISL. And based on the scan function, we have trained the potential, and this phase is thermodynamic stable. And the structure is shown here. It's a new topology. So if you try to find the structure with data mining, would not be helpful. But with those evolution, etc., we can get this structure. And now I want to continue my journey of what phrasing from homogeneous to heterogeneous. And the most famous, quite famous substance is silver iodide. And this is the normal processes. And on irregular silver iodide surface, we noticed that at this special region, unknown ice phase is formed. And we try to identify the structure of this phase and realized it's exactly fall into the ice territory that we have predicted among the 34 ice phases. We named it ice E, and this is how it was generated. And actually, because of those diverse hydrogen bonds, and especially the interactions between the liquid and the substance, we think maybe we should check the conventional ice nucleation process on flat silver iodide. And this is the result. You can see the free surface based on the deeper neural network potential, and compared with TIPP ice and lane joints potential connecting water and the substance is completely different. The active site here is surrounding iodine, and the one can see here is surrounding silver. And so, thanks to Sarah Ortiz Mason, and some of you maybe are very happy and accept our paper yesterday, the paper yesterday. And since we think we have crystallized water quite well, and I have amazing. How about crystallized Earth? Okay. During the evolution of our Earth, ever since the giant impact, there are two important phase transitions. One is core formation, the other is magma ocean crystallization. We have studied both processes. Today I will mention the magma ocean crystallization process. And for the magma ocean, the resulting mineral is bronzemanite, MgSiO3. The dominant mineral, and so we have trained the first the machine learning potential using multi-sample multivariate simulations, developed also in my class group, and construct a very powerful machine learning potential that can be functional to 220 GPascal, and based on our experience with many crystallization processes like water, we realized that if we want to fully understand the process, the liquid structure is the first step we need to do. And so, actually, the liquid structure is the starting point, and it really kinetically important to the evolution of the magma ocean. And the thing is that from the upper mantle to the lower mantle of our Earth, the pressure increases intensely, and so the density will increase enormously. But how the mechanism to govern the densification processes is also in debate. Some ascribe to the silicon polyhedral, and some to the coordination of oxygen. And there's another unique property about the silicon melt is about the viscosity. We all know that most of liquid, if we squeeze, the free volume will also decrease, so the viscosity will increase. But look at here, the viscosity will decrease until roughly 8 GPascal and increases again. We don't know, or we don't fully understand the structure or reason of it. And I think it's because we did a lot of work related to water. And at some point, my student Shui said, oh, okay, I think there's structural heterogeneity in this system, and it's characterized magnesium and silicon enriched region. And no matter from the IDF, experimentally, our simulation is matching quite well. Based on this idea, we have tried to track the evolution of those enriched regions, no matter magnesium or silicon. Look, the volume shrinks and increases with inversion. And we calculated the lifetime of those regions. It also shows this abnormal phenomenon. The lifetime decreases and increases. So it's probably the viscosity is connected with this interesting phenomenon. So we have calculated the viscosity, quite agreement with previous experiments and simulations, and we, based on the viscosity, we calculated the Maxwell relaxation time and compare directly with the lifetime of magnesium and silicon enriched regions without any change of units. You can see they are matching quite well, especially with the magnesium enriched regions. So it's like the magnesium increased region is the aligning region for those viscosity anomaly. So to prove this point, we add a bias, a wall, to eliminate the structural heterogeneity of the system, and then we recalculate the viscosity, then the anomaly disappeared. So we would say that structural heterogeneity is really the structural origin of this viscosity anomaly. And based on this, then we turn our attention to the nucleation processes, and it turns out this is extremely challenging. I tried many collective variables. You can try if you want to test your measures, structure factor works. I didn't find another other parameter works for this system. I don't know why, but this is how it is. And with forward flash sampling, and we get this very complex nucleation process, and we turn attention to the growth and the nucleation process. And interestingly, you can see that the growth is not a continuously steady process, but it's a stepwise growth. And occasionally, it can grow, and then melt, and then grow again. So it needs to rest for a while, and then continue to grow. The underlying for this is because the structural heterogeneity again. So if we continue these processes, I try to solve a big problem that in the earth science is about the grain size of the bridgemanite grains. That's because it will directly determine the evolution and convection of the deep earth. And based on this, we first estimated the critical size at different pressure and temperature, and then we have calculated the interfacial energy. And based on the interfacial energy, we found that it's a huge number. It's roughly 1 joule per meter square. And this will directly result in one information is about the grain size. Based on two models, the grain size we estimated is ranging from 0.1 to 1 meter. It's giant crystal grains, and before our work, previous literatures think that it's roughly around a millimeter. But in the earth science, they have demonstrated that there's a critical grain size. If it is big enough, then the convection model will be completely different. And so we have proposed a new model regarding the magma-ocean differentiation processes. First, bridgemanite crystals forms, in the deep earth, in the lower mantle of the lower mantle, and then it will float up to the neutral buoyancy layer, and then giant crystals from the bottom, and a little bit smaller molecule from the Earth, and eventually we'll get this differentiation processes that with time there will be some viscous convection, and that's the new way to understand the integral structure of our Earth. And actually, I'm sorry that it realized this time I talked quite fast, and I have still bit time, so I will mention another story. So we feel that we have to understand the earth and the water. Maybe it is enough to turn our attention to other systems, such as solid-solid phase transition. And this is a special case, titanium oxide. Titanium oxide is a special phase that it goes through a local reconstruction process, but it's super fast, ultra fast. But usually if it's reconstructed solid-solid phase transition, the kinetics is usually slow, and we don't know the reason. And so we have train potential and try to understand this process. Actually, it's a layer by layer phase transition process. In each layer, it's a two-dimensional growth, nucleation and a growth process. So it has divided the giant, big, and the barrier to several smaller energies. So I will back to my cases, summarize my talk, and I think with all those fascinated methods developed by Michaela's group and etc., and we can really understand the boundaries of extremely complicated nucleation processes, water, no matter homogeneous or heterogeneous, and our earth, the mineral, etc. And at the end, I would like to acknowledge Michaela, Atom, and my dear colleagues, friends Pablo, Michaela Ivanici, and Luigi Bonatti, and Deng Jie, and my students who are involved in those works, Mingyi, Yao Chen, Yue Feng, Junwei, Shiwei, and also my research group. And at the word end, I think I'm so lucky that I can join Michaela's group. It's a life change moment, and the opportunity is so precious for me. And thank you very much, and happy birthday to you, Michaela.
Thank you very much for your nice talk. Comments?
Yeah.
Where? Yeah, Sandra. You're very scattered now.
Thank you. Nice talk. Thank you. I was going back to the magnesium silicate. The drop-in viscosity in the case of silicates is actually well known in silicates, in liquid silicates, and actually it has been traditionally explained based on the transition of silicon coordination from 4-fold to 6-fold.
Yeah.
I mean, this is the way, for example, it is explained in pure silica.
Yeah, yeah.
How does this simple mechanism, connect with what you were just mentioning?
Okay, so it's I think it's a dual role processes. So for this multi-component system, the magnesium will breaking the silicon network. When I say the silicon network is silicon oxygen network. So in pure silica, the behavior will be different because the adding of those magnesium, it will create those regions with relatively low viscosity, and that's the reason why. Yeah.
Okay, I don't see any other raised hands, so we thank our speaker again for his nice talk.
Oh, sorry. Maybe I want to give another speech.
Yes.
They never understood me, huh? Thank you. All right, so I'm very grateful to the organizers to let me in this Parinello event, even though my talk is entirely without computation. But let me first go and spend a few words on my association with Michele. This goes all the way back to the days at IBM Zurich or Rüslikon. He got me there, saving me from a completely dead-end career in the Netherlands, and threw me right in the deep end of Parinello water. Well, that was a struggle. Systems were very, very small. I think some of you know this, 32 water molecules, just a nanometer box, and runs very short, 4 picoseconds, because it took a week to collect 1 picosecond. This was still CPMD. And yeah, you heard from Annabella's talk, things have scaled up. The system size now is about at least 2 orders of magnitude larger, run lengths in the nanoseconds. But I'm not doing machine learned potentials. I will talk about some thermodynamics. But I hope I can still connect to the modern Parinello world by talking about collective variables. Oh, this is new to me. So the question is, now we really change from the subtle, highly informative pictures of the previous speaker to the thermodynamics scale. Everything is washed out. But the question is, what is a collective variable that can distinguish a liquid from a solid? Obviously, shear elasticity. But is that all? Is there also a difference between a solid under hydrostatic stress and a liquid? Well, if you look at the atomistic picture, it's clear. You can see the vacancies. There aren't any vacancies in a liquid. But so that could be a good descriptor. However, I am more demanding. I want a thermodynamic state variable to be a descriptor. And vacancies are not thermodynamic state variables because there is no mass equilibrium between the liquid and the solid for vacancies. This is really rather disappointing. Now, the material scientists thought about this already since the 50s, and they decided that the number of lattice sites is a thermodynamic variable. Now, that takes a bit of a step, and it is formalized in this, what is called the Lache-Kahn network principle, and it says that the number of lattice sites is preserved under deformation and under the creation of a vacancy. So even if there is a vacancy, the number of lattice bonds don't break. And then you wonder, all right, so how can we change the number of lattice sites? And that can only be at the boundaries, in particular, the interface between a liquid and a solid. You see, my pictures are very, very simple. That is all you get to see. So here's the liquid, here's my crystal. There are m lattice sites. The volume of a cell is Vc. So the volume of the whole system is m times Vc. And if I then move the boundary, the volume gained by the solid is lost by the liquid, and the same for the number of particles. But there are 2 ways to move this interface. You can simply add a new row of particles. That is, you keep volume of the lattice cell fixed and increase the number of lattice sites. And then the number of particles is more or less the increase in the number of lattice sites. We do this under open conditions, so it might not be exactly the same. However, there's another way of doing this. You can simply stretch the crystal. Then the number of lattice sites is now the same. The volume of a cell changes. And now that again gives a change in volume. So
in this case, the number of particles basically remains the same. So there are two modes which will continuously return, but at least suggested to the material scientists, in particular this guy here is really influential, to treat M as a thermodynamic degree of freedom. So that means we have to add it to the Gibbs equation. Huh? So here is, I do this all isothermally, so no temperature change. There is the pressure term, the chemical potential term, and now there is another term. There's a new thermodynamic field, which I call nu, just for symmetry. It's the partial derivative at fixed n and v to m. So the question now is, what is this, and how to use it? All right, let's go back to this extended space, thermodynamic variable space, n, v, and now also m. I can make three densities, in addition to the standard particle density. There is now also a volume, cell volume, which is volume divided by the number of cells, and also occupation, the number of particles divided by the number of cells. There are three different variables, but two of them are only independent. So if I divide occupation by density, then I eliminate n, particle number, and I'm left with the volume of a cell. Now, this is highly alarming if you have a statistical background. I have now a variable that does not depend on the number of particles. This really is a big problem and has been divided out. Not for me, because I am doing only empirical microscopic theory. All right, so all three densities I just defined turn up in a free energy function. This is the Helmholtz free energy, which is a function of n, v, and m. There is an entropy term, an elastic term. That is where my whole cell volume is going to turn up, and a site binding term. The entropy term is the number of lattice sites times the entropy per site, for which I'm going to take the standard Langmuir entropy. This new term, the elastic term, is simply the quadratic or harmonic term in the stretch, where the stretch is the ratio of the actual volume per cell divided by some reference, whatever that is. And then, for good measure, I still retain a term which is only dependent on the density, on the particle density. And where does this term come from? Well, if you think about a mean field picture of binding energy, a kind of Kurt Binder picture, then if particles have a finite size, if I shrink the lattice, then of course the size of the particle stays the same. So a mean field treatment of binding energy would depend not on occupation, but on density. All right, you might say, okay, that's double counting, because there's already interaction in the bonds. Again, at an empirical constitutive level, I'm not going to worry about it, but a statistical mechanical person should. All right, so now, if I then turn this representation in what is in material science is a standard way of writing in a per cell, a per site representation, there is the entropy per site, the elastic energy per site, and also the binding energy site. There was an n in front, but I divide by m, I multiply it by c. Now this thing is explicitly extensive, right? None of the densities changes because they're ratios of the extensive variables, and only the prefactor that determines the size scales with a lambda. So this thing is explicitly extensive. So that means that we can go through the normal Gibbs procedure and apply Euler's equation. So here is again the Gibbs equation. This is the what I call the first order homogeneous property, and then the normal argument is applying Euler equation. You can write it as minus PV plus mu n plus this now additional term. So if I bring this to the left-hand side, then on the right-hand side would be something that is normally 0 in a liquid, but maybe not in a solid. And this thing has been introduced way back by Guggenheim, but he didn't quite know what to do with it. now the claim of basically Kahn is that it does play a role in an elastic problem. So what could this, but this has severe consequences for the thermodynamics. Here's my equation again. So if you now normally define the Gibbs free energy as F plus PV, and you take the molar entropy, then it's no longer equal to the chemical potential. There is this gap proportional to this nu. And the same for the grand potential density. It's no longer equal to P or minus P. There is this nu. So now the question is this nu zero or not? I already put in the paper, and all my physical chemist colleagues, including all the referees, say it must be zero. It's not. You can see that if I go back again to the Gibbs equation with my extra term, what I call the integral Gibbs to Hem relation, then I can determine a Gibbs isotherm. The nu is a total differential, I divide by m, and then the partial derivative with respect to chemical potential at constant pressure and temperature is the cell volume, so is the occupation, and the same for the partial derivative with respect to pressure. This is the cell volume. And these things are observable, so you can get them out of the diffraction spectrum. They're certainly not zero. So this change in U can be determined by thermodynamic integration. If I ever get back to computing, that is what I should do, right, on some simple model. So this nu is not going to be zero. And then you can say, no, is that going to matter for the normal properties that I'm interested in? So let's have a look at the chemical potential. So here's my equation again, my expression for the Helmholtz free energy, entropy term, which is only a function of N and M, elastic term of V and M, and the site binding energy of N and V. So if I then determine the chemical potential the normal way by taking the partial derivative of fixed V and M, then I find that there is no contribution of the elastic term because it didn't contain M. V over M does not contain N. You can work out the first term, which is the Langmuir entropy. The second term is a bit more effort, but you recognize the standard expression for pressure of liquids. There is a linear, normal binding term plus its derivative with respect to density. Fine, but there is no elastic term. And this is a major problem. Already Landau and Lifshitz complain about it. How to define a chemical potential for a continuum elastic system. All right, so where did the elastic term go? Of course, it must be in this new variable. I called it lattice potential. That's not a good name, but I will keep it for the moment. It actually is a material pressure, if you know what that is, but I'm not going to call it that way. All right, so now same thing. Nu is F differentiated to M at constant N and V. Certainly the entropy is still dependent on M. The elastic energy does, because it was V divided by M. But now my binding energy drops out because there is no M. That you can work out. I spare you it. You get a rather simple expression. This nu is the logarithm of essentially the vacancy population, 1 minus C, and this term, which you can linearize straight away to the volume stress. J plus 1 divided by 2 is 1 in the linear approximation. So this equation can be easily understood. What happens? What was new? You increase the number of lattice sites at fixed particle number and volume. So the number of particles stays the same. So you create vacancies. They got more sites and they must be empty. But also, since volume is changed, you compress the cell volume. So there is also an elastic term. So this term links vacancies to volume elasticity. Again, this is known in material science by Herring already said this. Herring is it's the same Herring you know. It is was a very very versatile man. Unfortunately, most of his papers were published in proceedings, which are not easily to get. Possibly Mike can find them. He seems very talented in this. All right. So do we need this new? Yes, we certainly need it, because there you see, you already saw that. The chemical potential diverges in the limit of a perfect crystal. The vacancies are in the numerator. On the other hand, there is the same divergency in this new, the opposite one. So if I add them properly, according to the Gibbs to Hem relation, n plus mu plus m, this divergence, this ideal crystal divergence cancels. And the entropy, of course, as you know, is well behaved in the c equals 1 limit. So you really need, this was another problem of the chemical potential in a solid. It seems to diverge in the limit of a perfect solid. This is a big struggle in solid state chemistry. In the books, they warn you for it, for instance, Nix and Cao. All right, so now, I'm going too fast. Now the pressure. There now the two terms are combined. I have to differentiate now to respect to volume at constant nmm. Now the entropy cancels. It's weird, but I define the entropy as a occupation and not as a density. So here it really disappears, and I'm left with the elasticity term and the binding energy term. Again, you can work it out, not so difficult. I scale pressure now because I make it in an energy. I multiply by the reference cell volume. And then there are two terms, a molecular term, which comes from the derivative of this density-dependent binding energy, and the elastic term, which now is, without any approximation, the volume stress, alpha, which is the elastic constant, times the strain, J minus 1. No configurational entropy, I'm not going to worry about it, but there of course is. It's hidden in this free volume that is in this derivative. Okay, so now we have a strange situation, because the pressure consists out of two different terms. In mechanical equilibrium, it must be equal to the applied pressure. I put a bar, that means applied pressure. The star meant that it was scaled. And in our two terms, so at zero pressure, I have still a finite molecular pressure and elastic strain. And you can convert the density into a function of the occupation and the stretch. I have repeated the equations here, but you basically eliminate m. So there is now an equation for fixed occupation for the strain or the stretch, and you'll find that at zero pressure, there is a finite elastic deformation, which is due to the coupling to mass density and elasticity. Again, this is known, it's called eigenstrain, and you can make it very, very difficult, as usually happens in continuum mechanics papers. But already this simple model shows this. It can be rather large, right? But if you only, in alloys, if you only have vacancies, it's not very big. All right, I'm approaching the end. Here is my review of this all-important Lachey-Kahn network principle. A solid allows for open system expansion, conserving the number of lattice sites. So that means that the change in mass density is essentially the geometric change in volume. There's a little correction due to an open system exchange, creation of vacancies, but as you can easily see coming, this must be proportional to the vacancy population. If there is anything left to fill up, nothing will happen. And there's also accretion. You add the same number of cells. And this is all that happens in a liquid. There is no change in density. And in a liquid, you automatically fill up the space under open system expansion. But in a solid, there is this alternative. Okay, I'll end with my congratulation graph, if I can find it. Yes. Congratulations, and as many of you already have said, please carry on. And well, to me, the main stimulating example is you never give up on a difficult problem. And I think here you have another difficult problem. I think you haven't solved it yet. Thank you.
Well, Michiel, are there questions, comments? Yeah, Alessandro.
I will dare to ask a question. Let me put it in this way. So here, all of these things sounds to me like the physics of vacancies, in the sense that you basically have a perfect crystal, then you start adding one vacancy, and then you have an entropy related to the presence of a single, let's call it quasi-particle, which is this vacancy. Then you have two vacancies or three vacancies, and all of these adding vacancies creates an entropic contribution which plays a role. Did I capture?
No, this picture, the difficulty is that the vacancy is not a chemical species.
It's not,
yes. No, you cannot exchange it with a reservoir. This is the struggle in material science, and that's why they choose the number of lattice heights to be the thermodynamic variable. Now, in density, classical density functional theory, people are trying to do what you're saying. If you know these people in Germany, Fuchs, and also Gerhard Kahl in Vienna, and they get stuck for this reason. So this Lachey-Kahn is not a joke, right? This literature is a bit ignored in physical chemistry, and this led to a problem, because maybe you know, Swoop and Anderson had a way of calculating the vacancy. Now I'm going to say something dangerous. A way of calculating the vacancy creation energy, and they optimized in the cell volume, which is forbidden in the Lachey-Kahn. So the Swoop-Anderson procedure violates elasticity. I wrote that in my paper. It got rejected, and it took me 10 months to get it through, because it disagrees with Anderson. But this Hans Anderson, he wrote this in 1992, and this was already very well known. This paper is from '73, so this is a typical example of our communities not reading each other's papers. This is the standard paper, right, but not the best.
Next question.
Thank you, Mike, for the nice talk. One question concerning the new variable you have introduced, which is the number of lattice size, which is an integer variable. Those derivatives that you have defined to get the potentials, they have discontinuities as we are usually having in density functional theory when you increase the number of particles, because they have to be exactly integer numbers, and then you have to go to a more grand canonical approach.
This is exactly what also these classical density functional people are struggling with. This is, I all the time assume the system is homogeneous, right? So to the extrapolation to the inhomogeneous system, to make this a local variable is not easy. And indeed, Matthias Fuchs is running in divergences, so that direct correlation function, the ones in the Ornstein-Zernicke equation, is divergence like hell. There is a problem similar to, In fact, in my paper, I call the number of vacancies H, because there is a clear correspondence between semiconductor holes and this problem. They haven't solved it yet. I wrote them. I'm in contact with them, but I don't know what happened.
Thanks. More questions? Comments? We raise hand, and we thank Michiel for his talk. And we will take a coffee break. at 11:10.
Yes.
I just want to test my computer.
Yes.
I don't want to interrupt you, but it's a good time. I don't want to have to deal with this at the very end of the day when nothing.
You are talking after me?
No, yeah, but I'm the last talk of the day.
Yeah.
But I don't want to. I just want to.
It can be tricky. Yeah, with also on my Mac last
Yeah.
time.
So I guess what do we plug? Oh, I guess we can use this.
This one for me it did not work. Try, but
So I need a plug-in, I guess, or.
Chris, I have this
Me
one,
too.
and this one works. I
Yeah,
tried.
I think. Let me just see if. I'm sorry. Well, I'll use yours right now just to test mine.
yeah.
And then, worst case, and then I know I have one of these in my backpack too. So let me.
2 months ago, I was in Washington D.C. on a conference, and and also with I had a different adapter.
Right.
No way to get it working.
No,
Absolutely
God,
impossible.
that's scary.
And
That's-
someone borrowed me this one, and then when I came back home, I immediately bought this one. This other one.
Exactly. So
Because,
I start from
I
here.
have to go to this place and say
Start from
extend. Yeah.
Here. Okay.
Yeah, it
That's
works,
it.
it works,
Yeah.
it
Let me
works.
just look at. And I just then the last thing, and I'll give it back to you. I apologize. You're being very nice to me. I just want to put it into the because now I want to see if I'm in display mode. If I go and get my pointer, because I think the best way to do things is just to you can is just to sit here and sort of just give the lecture here and then just point with this rather than. Okay, I think I'm done.
I
That
will
works.
use the lesson.
Okay, I appreciate it. Very kind.
Let me try it now.
Yes.
And at our university, at our lecture room, for whole year, this did not work at all. I could not connect it, and now I said that when the semester finished, I said that I'm going to investigate what is the problem. It was the cable. The cable didn't work.
Well, it didn't work.
It worked with some laptops, but
Right.
not with this one. Not
Yeah.
with this one.
Oh my God.
So, let me switch this Wi-Fi. Yeah.
Hey. And you're in presenter mode too,
Yeah.
which I like.
Yes.
So
Okay. I
good.
show this pictures
Oh yeah.
and also movies. Yes, I show this historic movie.
Yeah. Oh, this is good stuff. Very good. You're
Good.
set.
It works. Yeah, fantastic. And let me
We
check
both-
the
yeah.
check the point. Carla borrowed me
Yeah, I'm just going to use, I think,
this thing. So,
it's good. Oh, Carla has a fancy. No, that's
like
the-
this. Okay, perfect. Yeah, and can you see? Yeah,
Looks good.
yeah, very good.
Very good.
Okay, perfect.
essenzialmente la transizione dalla fase ferroelettrica alla fase paraelettrica è una transizione a primo ordine, ma non è descritta dalla teoria classica della nucleazione, perché il fatto è che la fase paraelettrica è una fase che ha una struttura cristallina diversa, e c'è uno strain che la coesistenza tra questa fase ferroelettrica e la fase paraelettrica, se abbiamo una coesistenza macroscopica, quindi che è necessaria per la realizzazione di una superficie di separazione tra un nucleo macroscopico e una fase e un'altra fase, questa coesistenza è impedita dalla strain che è dovuto al fatto che i lattice parametri delle fasi sono diversi, e quindi il sistema preferisce nucleare a livello nanoscale e quindi non è descritta dalla teoria classica della nucleazione. Questa è una cosa che si traballo, e poi aggiungo un'altra cosa recente che abbiamo fatto, che è quello di
I'm pretty sure it'll work because I have given a talk on the same system here before.
descriviamo direttamente un elettrone
I need
You adapter, yes.
I have one of these.
questo combiniamo questo machine learning con robe che hanno fatto tantissimi anni fa, quando Michele ed altri, Annabella e Paolo Carnevale hanno studiato l'elettrone.
So, we need to connect this video here. And put it back. Everything looks fine. Do you have animations? No. Okay, then I think you're fine.
Is that okay?
Yeah. This is gonna be your pointer, the one on the bottom. Try it up. No, the one on the bottom. Okay. Then we
I don't need one of these. No, it's okay. I can
You
just.
can leave this here and this.
Okay.
Yeah, I'll just put it back. And this is gonna be your mic. This one.
Okay. No worries.
Okay.
We'll take it.
Posso dirle tutte e due, ma molto rapidamente, essenzialmente. Sì. Sì. Ok.
Better than hold it in my hand.
Much.
Entangled, yeah. Not quantum entanglement.
No, unfortunately.
This is classical.
Yes. Help me? Yeah.
This goes in the pocket.
Yep.
Should be okay like this?
Yeah. A bit tap, maybe back right. It's also okay. Like this.
Like this? Bene.
Sono questi tipi? Sono i tuoi colleghi?
Oh, they produce the machine learning. Machine learning potential for carbon at terapascal pressure. So they gave it to me and I did. There are molecular dynamics people.
So this continues the thing that you always propose to do, right? So you do it.
Absolutely.
I see.
My new PhD.
You have some bright new student?
He's good. He's good. I'm really happy with him. Now I'm gonna have the Indian postdoc from November.
Welcome back to the second part of this morning session. I'd like to introduce Roman Martonak from the Comenius University in Bratislava, who's going to uncover for us kinetic pathways of pressure-induced structural phase transition by metadynamics. Martonak, please.
Thank you very much, Paolo. I would like to thank the organizers for the invitation and for the opportunity to come here and participate on this great and fantastic celebration of Michele's birthday. It's a great pleasure and also great honor for me to be here. And I would like to present some recent work done in Bratislava together with my PhD student David Vrba and also together with the group of Ivan Olejnik from the University of South Florida. I spent altogether 7 years with Michele, first 2 years in Stuttgart, 98 and 99, and then other 5 years in Lugano from 2001 till 2006. Unfortunately, I discovered that I have almost 0 photos with Michele, so this is in fact the only one that I can show. It was provided to me by Matteo Ceccarelli. It was already shown at this conference, and I am not able to find any more. But what I would like to show are some pictures that I produced after I bought in 2003 in Switzerland my first digital camera and learned how to make panoramas. It was not as easy as now. Now it is one click on a mobile phone. This was handmade, manually selected control points and all, straighten the horizon and so on. It was a lot of work. But so this is meant to show how beautiful Lugano and all this Ticino region really is. Okay, so I will first provide some introduction. Why do we go from prediction of crystal structure to uncovering of kinetic pathways? And I will show the approach on 2 examples. First is silica, and second is carbon at terapascal pressures. So let me show the introduction. So all this is concerned with polymorphism in solids, which is well known. We can have for the same composition more crystalline forms with very different structure and different properties. They are often metastable outside their thermodynamic stability range, which is well illustrated by the example of graphite and carbon. In fact, there should be no diamond. Graphite and diamond, diamond should not exist at ambient condition because it's only metastable, yet it persists on a geological time scale. Now, there are basically two things that one can do about polymorphism. One is to focus on crystal structure prediction and search for the phases, and the other is instead to focus on the transition from A to B, from one phase to another. Now, concerning the first approach, since starting roughly 20 years ago, there's been a huge revolution, starting with the work by Oganov and Glass, evolutionary algorithm. Also, at the same time, Picard and Neitz developed the random search approach. And these both were extremely successful, and there are also many other variants of these and combinations of these approaches. I'm not going to talk about this. They also have been generalized to variable stoichiometry, multi-objective optimization, and whatever other branches. As a result of this development, huge number of structures were predicted. However, only a fraction of them has been seen or prepared or synthesized experimentally. And it turns out that there are many structures with useful properties, desirable properties, which are metastable. And therefore, one would like to understand how to get to these structures. And for this reason, understanding of kinetic pathways, possibly ultimately control of structural transition by controlling the pathways is we believe is critically important. The fact that kinetics is important is very easily shown on the super simple example of silicon. When we compress the cubic diamond structure to 11 gigapascal, it turns into beta tin, which is metallic, but upon further decompression, it does not come back at room temperature, it does not come back to cubic diamond, but it goes into a metastable BC8 phase. And this has been known since 60 years, published in this paper. Now, if one wants to simulate the structural transition, there are several possible approaches. I start with the simplest ones, which are the static approaches based on geometric modeling, group theory. They can be very, very instructive, however, have their own limitations, because they provide only a collective mechanism by construction and work at t equals 0, so there are no entropic effects at all. It's much better to use some kind of dynamic approach, and that has been pioneered by Michele long ago with the Parinel-Raman variable cell MD, which was the first technology that enabled to simulate structural phase transitions. And then we combined this in the early period of metadynamics. We combined this with the supercell collective variable, and it was applied to many materials, also in combination with ab initio. Of course, it has also its problem, because it uses a 6D collective variable. It does not allow to calculate the Gibbs free energy profile. And also, by construction, these supercell vectors are global variables. They do not allow to address nucleation. And there have been, over the years, many other constructions of collective variables. I mentioned here some of them. Also, the problem can be addressed by transition path sampling. Just for nostalgic reasons, I show here a piece of this nowadays historic movie produced by Paolo Raiteri, who gave his talk the other day here. And this was simulation of solid benzene, where we started from one of the known phases and started the metadynamics. And by miracle, this produced several other phases. Now, I think you will see several other transitions. So now it comes back, but in a moment it will start fluctuating strongly, and then there will be two new phases, one after another, very, very quickly. So it's almost there, I think. Yes. Now this will be the first transition. Yeah. Now there will be a second transition, and so on. So this is something that made us very happy in 2005, but still one would like to use somehow better collective variable. And of course, it's impossible to design one which is completely universal for all structural transition, although it would be fantastic to have something that is simple. But still, one wants to keep it as simple and generic as possible, and not biased towards any particular state, in order to have a predictive power that we start from A, but we don't know the B. And obviously, the dimensionality should be low, so ideally two-dimensional, at most three-dimensional. Fortunately, high-pressure physics or high-pressure crystal chemistry gives us some rule. There are some 10 general rules of high pressure, and the rule number 4, published in this paper, says that increasing pressure increases coordination number. I would like to add that usually increases. It's not always the case. Calcium for example, goes the opposite way. It decreases the coordination number. But let's say it changes the coordination number, almost always changes the coordination number. And in fact, coordination number was already used in one of the early works that we did with Marco Bernasconi and Federico Zipoli in 2004 in the simulation of graphite to diamond transition. And recently, 4 years ago, my student Matej Badin also applied coordination number in a study of a toy model of the B1, B2 transition in sodium chloride. This is a system, supercell with 64,000 atoms of sodium chloride. And here you see, so the color refers to coordination from 6 to 8, as is shown here. And now you will see how the system attempts to create the nucleus of the new phase, tries, and then it dissolves again, tries several times, and then upon a certain point it reaches a critical size, and the new phase takes over the whole system. Okay. So after this introduction, now I would like to show the two examples. The first refers to silica. Silica is a well-known and highly important system. Here are just some of the important phases like alpha quartz, alpha cristobalite, coesite, and stishovite. Silica is important for geophysics, planetary science, and so on. It has very rich polymorphism, many tetrahedral phases, quartz, cristobalite, coesite. Coesite is shown here. It is the most dense and most complex tetrahedral phase. I think it's obvious already from this visual inspection of the unit cell. The conventional unit cell counts 48 atoms, so it's a pretty big system. What happens when one compresses these tetrahedral phases? Typically, the coordination number, SIO coordination number, changes from 4 to 6, and instead of tetrahedral phases, we get octahedral phases. This, of course, is important to understand the processes that take place upon impact of asteroids or meteorites on the Earth's surface. And there is theory known since long time, 1998, what the octahedral phases of silica look like. They are based on the oxygen HCP sublattice, which is half filled with silicon atoms, and some examples which these silicon atoms, these octahedra, are organized into chains, and these chains follow typically some regular pattern, which can be defined by the periodicity of these kinks. So this, for example, is stishovite, which has no kinks. The other extreme case is the alpha PbO2 like silica, which has 2 by 2 kinks. This will be very important in the following discussion. Now, we focus specifically on the compression of coesite, which is interesting because it's a complex structure. Different outcomes were found by different groups at different times. So first, amorphization at 34 gigapascal by Hemley long ago. Then another experiment by Hu et al. 2015 was a transition to what they call high-pressure octahedral structure at 40 GPa. Now, these are irrelevant for this discussion because it's just periodic modulation. But this is, again, a reconstructive transition. This is the most recent result, 2018, by Bikova and co-workers in Bayreuth, transition to coesite 4 and coesite 5 beyond 30 GPa. This is coesite 4, this is coesite 5. What is interesting that this structure is really very strange. It is highly complex. It violates at least 2 of the polling rules, mainly the third polling rule, which states that octahedra should not be sharing a common phase. Here one can find precisely such situation. And as a consequence of this, it has a high enthalpy of nearly 0.4 EV per atom over the ground state. So normally one would say that this structure should not exist. It's a miracle that one can even see this. And as the authors said explicitly in their paper, that the very large differences in enthalpy between phases indicate that using modern algorithms of crystal structure prediction or ND simulation, it would be highly difficult, if possible at all, to find these phases. Okay. Now, let me show the existing simulations of coesite compression. Actually, I think the first one was done by us here in Lugano in early days. This was ab initio CPMD metadynamics on a single unit cell with 48 atoms. And it is shown in this, the evolution is shown in this figure, and we found a transformation to the alpha PbO2-like phase. Then in the group of Sandro Scandolo, this NPT-MD was performed in 2017, and the result was that several multiple pathways were found, something similar to what was found in one of the experiments, HPO, actually defective alpha-PBO2, and also amorphization was observed. And in the same experimental paper, they also performed, Hu et al. Also performed CPMD metadynamics, actually using SIO coordination number as CV plus some unit cell parameters, and they found an HPO structure with a diffraction pattern similar to what they observed in the experiment. Unfortunately, they don't show the structure. There is no structure provided within the paper, so one cannot really compare. Now let me show what we did. So we used silicon. So we used NPT-MD plus metadynamics, LAMPS, Plamet. We used a very recent and super fast ACE machine learning potential developed last year by Erhardt and coworkers, and used an SIO coordination number and volume as CV, and performed a simulation on system of coesite 2 with more than 1,500 atoms at 35 gigapascal. Repeated the simulation 10 times with different initialization of velocities at 3,000 and the same at 300 Kelvin and the same at 600 Kelvin. And here is the outcome. We found about half of the cases we found a disordered structure, but at 300 we found also once this high pressure octahedral, and 3 times a transition directly to this coesite 4, exactly the same as found experimentally by the authors who believe that it cannot be found in computational procedure. At 600 Kelvin it is just the opposite. There was 4 times the HPO and 1 time, only once the coesite 4. So let me start with the transition to the HPO. So the key ingredient is the formation of an HCP sublattice, as it should be, which is accompanied by densification of the system and enthalpy drop by 0.2 eV per atom that can be seen here. And this is the drop of the number of oxygen atoms which are in the HCP sublattice. Now this is the evolution of the system. And what is found at the end of this simulation is in fact a system which has a nearly perfect HCP sublattice of oxygen atoms, but very imperfect organization of the silicon atoms in chains. So here one can see the chains in one of the planes, and one can see that they are basically disordered. There is no regular pattern, and that's why it has enthalpy 0.2 eV above the ground state. And then we wanted to see, so in order to get to a regular pattern, one needs diffusion of silicon atoms to make some better organized chains. And we simulated this by other metadynamics with silicon coordination numbers. I'm not going into details, but we observed further ordering of the atoms, and in the end, they almost approached the 2 by 2 pattern characteristic of the alpha PBO2 structure. Also, the X-ray diffraction pattern approached the one which was observed in the experiment, and the enthalpy further decreased. So this is one of the observed pathway. And the other one was actually kind of simpler. So because this transition to this complicated coesite 4 is a fast one-step process. However, enthalpy drops only by 0.066 eV. This is what it looks like. And finally, to conclude this part, so we observed all experimentally observed pathways: amorphization, HPO, and coesite 4. We found that at low temperature it is the formation of coesite 4, which is more likely. At higher temperature it is the formation of the HPO, and ultimately converging towards the alpha PBO2, which is the preferred. And these two pathways are very different. As one can see on this enthalpy graph, in fact, this shows that coesite 4 is, I would call it a shallow pathway, because it stays on top of the surface, and it only does not go deep down in enthalpy. Instead, this other pathways goes much deeper. Okay, so this was the first example. The second part is related to carbon at terapascal pressure. Most people are interested how to make diamonds. In fact, we are interested how to destroy diamonds. It's somehow strange. Everybody knows that it can be easily destroyed by temperature. I think Roberto simulated this in the early years of CPMD. But we would like to destroy by pressure. And then the question is, what is beyond the diamond? And the most complicated, not only what is beyond, but how to get there. And this is still a major open problem in the high pressure physics. How to go from this cubic diamond to something else. Okay. So the question, what is the first post-diamond phase, was answered long ago. In 1984, actually predicted that it is the BC8 phase. Of course, at that time there was no evolutionary algorithm, so he only by intuition he took the BC8 phase that was already known from silicon, and showed that it becomes thermodynamically preferred to cubic diamond around 1 terapascal, which is 10 megabar, 10 million atmospheric pressures. Then the other phase is super simple. Beyond 3 terapascal, it is the simple cubic phase, which should become stable. However, obviously, these pressures are huge. These pressures are not easily attainable in any static experiment. No diamond anvil cell will bring you to this pressure. However, there is a technology which is called ramp compression. I have no time to discuss the details. And the experiments have been attempted several or probably maybe many times by now, and reported in this paper. And in fact, the highest pressure reached was 2 terapascal, so twice the transition pressure. Nothing happened to cubic diamond. Cubic diamond survived up to 2 terapascal, and this clearly points to the importance of kinetic effects, and also to the fact that we do not understand these kinetic effects really well. Recently, using a machine learning potential in the group of Ivan Olejnik, they simulated a very large system with defects and cubic diamond with grain boundaries and so on, and observed a transition from cubic diamond to BC8 at 2 terapascal and around 4,500 up to 5,000 Kelvin. And they showed that, in fact, there is an intermediate phase which is disordered or some kind of supercooled liquid. So here we wanted to address the other extreme case. So they had many defects which allowed them to observe the transition on a short nanosecond time scale of plain molecular dynamics. Instead, here we want to address the regime of homogeneous nucleation in an ideal crystal, which of course we know it's a bit unphysical. In a real system there are always defects, but we thought it would be instructive to understand what happens in this regime. And we use 2 coordination numbers as no volume, just 2 coordination numbers as collective variable, one with switching function like this, targeting just the region beyond the first shell, and second targeting the region just before the second shell. The same machine learning potential that they produced in 2022. And we worked on a system with 4,096 atoms. Again, used Plummet and labs, and worked at pressures from 1.5 to 2.1 terapascal, and on a grid 2,500 to up to 5,000 Kelvin temperature. And now let me show what, I will show you now 6 movies which show different transition upon different conditions. So this is cubic diamond to BC8 at 1.5 terapascal and 4,000 Kelvin. So these are to be regarded as kind of typical result that we found. I would like to note that the time here, the movie is not linear in time, but it focuses on the interesting, so it goes quickly through the less interesting parts of the trajectory and focuses on the ones which are more interesting. So let's see what happens. Green is cubic diamond, and we see now at certain point the nucleation of this disordered droplet that will be blue. This counts like several hundred atoms, and one can see now that this very quickly crystallizes into the red, and the red is exactly the BC8 that one is after. And once BC8 is created, then it spreads out over the whole system because it's thermodynamically stable phase at these conditions. The estimated barrier is about 500 eV. This might explain why people did not find anything in the experiment. So clearly, this is a difficult transition, and the presence of defects is absolutely crucial. Then we increase the pressure slightly to 1.8 terapascal, and at this higher pressure, the system is closer to the phase boundary with the simple cubic, approaches the simple cubic, and now we will see a very funny thing. So again, starting from cubic diamond, again a disordered droplet is created, but now instead the first solid phase that will be crystallized from this disordered droplet is the simple cubic. This part is simple cubic. It has been rigorously analyzed by a phase recognition algorithm trained to all these phases. It's well visible in a different orientation by your eye, but not from this view, but it is simple cubic. Then when one continues, then this simple cubic immediately melts and then immediately crystallizes to BC8, and then the BC8 in the same manner as in the previous case spreads, takes over the whole system. So one observes really very complex and very unusual processes during the nucleation. Okay, the next case is yet higher pressure. It's 2.1 terapascal, and in fact, in this case, as you will see, there is no more BC8 being created. Instead, this goes directly to the simple cubic. You will see simple cubic is nucleated from the disordered droplet, and this spreads to a whole layer in the system across the periodic boundary conditions. Then it takes a while. It stays like this, and then in a moment it will spread in the Z direction, and it will take over the spread. The simple cubic will take the whole system. Okay, so now this is the end. What is important is that this observation puts an upper limit to the pressure where BC8 can be directly formed from the cubic diamond. So if one overshoots in the experiment, BC8 will be skipped. Instead, the simple cubic will be formed from cubic diamond. So then, interesting question is what happens upon decompression? Will upon decompression BC8 be recovered from simple cubic or not? There's no obvious answer to this. So we try to, but before going to that, I show another interesting point that, cubic diamond is not the only diamond. It's well known that there is also hexagonal diamond. It actually exists as a rare mineral. It's called lonsdaleite. It is metastable. It has the same local tetrahedral structure as cubic diamond. It's metastable with respect to cubic diamond, and therefore it's likely we expect more prone to transform. And this is what happens when you compress the hexagonal diamond. And now you will see basically it's very similar to what we observed before, disordered droplet, but now look at the time. I mean, this barely moves. This transition is actually, the movie is slow, but the transition is super fast. This transition is much faster than the transition, once it starts, it's much faster than the transition in cubic diamond. And also what is interesting that there is you probably noticed there is a well-defined orientation between the axes. So this is the 1-1-1. What you see is the 1-1-1 axis of the BC8 structure. It is parallel to the hexagonal axis of the hexagonal diamond, which suggests a strong influence of the matrix of the hexagonal diamond in this process. Okay, now I show the back transformation, so how to get from simple cubic to BC8 upon decompression to 1.5 terapascal at 3,500 Kelvin. So now the starting is simple cubic, and this simple cubic surprisingly transformed into a new phase which we never saw before, which to our knowledge is not described, has not been described in literature, has a very unusual space group P222. It's orthorhombic, very complex structure. And this then subsequently, as expected, this transforms into BC8. So we found a new intermediate structure on the way from simple cubic to BC8, which is shown on this figure. And I think we have seen in one of the previous talks, we have seen some ice L or something, or some new ice structure, which very much, this structural motif reminds me of this piece here. Okay. Now, the last movie. So imagine we are lucky and the machine manages to produce BC8 at this terapascal condition. Is it quenchable to ambient pressure or not? This is a long-standing question, whether if we have this phase, whether we could study and presumably, hopefully fabricate it at ambient conditions or not. There's a very good, I like very, very much this old paper by Mayotte and McMahon, published in 1991, very, very long ago. And they did a very deep analysis of the structural relations using group theory, and predicted that BC8 should transform preferentially to hexagonal diamond, more easily to hexagonal diamond rather than to cubic diamond. They basically counted the number of broken bonds and concluded that it's less difficult to go to hexagonal than to cubic. Now, I tried this decompression at 200 GPa, that is still 2 megabar and 3000 Kelvin, and this is what happens. We found actually this is not really disordered. I would say this is a sort of the appearance of the blue. I would say it is already diamond, but it is detected as disordered because it is heavily distorted. Now you will see that in a moment. Yeah, okay. This is diamond. This is a mixture of cubic diamond and layers of intertwined with layers of hexagonal diamond. The transformation barrier was still at 2000 gigapascal, was about 70 eV. This was a system of only 1024 atoms. At 100 GPa and 3000 Kelvin, the BC8 is no more stable within molecular dynamics, plain molecular dynamics. It goes again into mixture of cubic and hexagonal diamond. But at ambient temperature, at zero pressure, BC8 actually survived a 5 nanosecond plain MD simulation. So this shows that maybe it is indeed dynamically stable, and perhaps it might be possible to recover it at the ambient condition. So to summarize, what are the optimal conditions to find the BC8? So this is shown here in the phase diagram. This summarizes all the transitions that I described. So with increasing pressure, the barrier decreases, so it should be more easier. But then beyond 2 terapascal, BC8 is unlikely to form because the simple cubic takes over. With decreasing temperature, also I did not show that, but below 3000 Kelvin, we did not observe any of these transitions that go to BC8. Likely because of the fact that this disorder phase cannot be created below 3000 Kelvin. So this interval, so slightly below 2 terapascal and above, certainly above 3000 Kelvin, seems to be a good condition to find the BC8. And it might be easier start from hexagonal rather than from cubic diamond. Upon decompression, simple cubic converts via this intermediate new phase to BC8, and possibly BC8 might be recovered at ambient conditions. So let me conclude concerning the methodology. It seems that simple generic CVs such as coordination numbers work for pressure-induced structural transitions, not only in sodium chloride but even in much more complex systems with rich polymorphism, under conditions of high temperature where entropy plays a crucial role, and several ordered and even disordered phases compete for stability. And uncovering kinetic pathways in complex solid-solid transition pushes the predictive power of simulation much beyond the plain crystal structure prediction. Finally, I would like to say that all this work would be absolutely impossible without the landmark achievements of Michele, because all three crucial ingredients on which this is based relate to him: the variable cell MD, the metadynamics, and the machine learning potential. So Michele, happy birthday, and many thanks for everything, for teaching me and for helping me. Thank you very much.
Thank you, Roman. Questions? I saw you.
Thank you, Roman. Very nice talk. You alluded to the possibility that there exists a transition path between hexagonal diamond and BC8
yes.
at some point, right? But then if you look at, when you looked at the phase transformation, it went through a nucleation and a disordered structure close to the interface. So what is the interplay? I mean, what is the role of a transition path when, you know, the interface is actually disordered?
It's hard to say. I mean, it's a complicated thing, because this what is shown as blue as disorder is really stays there for very, very short time. It might be disordered, it might be just kind of interface or something, and then this BC8 just spreads very, very fast. I don't have a detailed analysis of the transformation mechanism, but so I am not able to say whether it is a kind of solid with an interface, or it is really mediated via this intermediate liquid. But it looked different than the cubic diamond starting material.
Yeah. Final question by Michiel.
I may have missed it, but can you actually create a stable coexistence?
Stable?
Coexistence between two phases. They always flash from one phase to the other.
Yeah, sure, because it was a strong overpressurization. It was
So my question is, can you create a coexistence?
I think yes, but that would be a huge barrier, of course, because you would be at equilibrium pressure. That would be a huge barrier. You will see no nucleation because the critical nucleus would be infinite. So you would probably go via some collective mechanism in a big system. Certainly, this is not something that the experimentalists are interested in, because already at overpressurization by factor of 2, they don't see nothing. They see nothing. So if you are at equilibrium pressure, you are. I see. Okay, maybe we can discuss later.
Thank you, Roman, again. It's a very nice talk. Microphone, Ali? Please.
Thank you, and let me say it's such a great pleasure to be here. I would say one of the luckiest incidents in my life was to meet Michele. I think it was 1991, and he's certainly been one of the most influential people for me intellectually, in terms of for many reasons, but also for giving one the confidence to tackle any problem. Maybe misplaced, incidentally, but there it is. Indeed, yeah. So I always show this slide. This is the problem that we want to solve. And I just want to put 3 observations here. I hope they're not controversial. Whether you believe it's very important or not, I leave it to you. I believe it's very important. Secondly, progress in the field has been painfully slow. Forget the hype. Essentially, very little has happened in the case of quantum chemistry since the 1960s, the case of QMC since roughly 1970s. And the third is that Michele has studiously avoided it, and I think these 2 statements are strongly correlated with each other. However, there is a glimmer of hope. There is a glimmer of hope. Yesterday, Michele finished his talk by saying, forget configurations, forget even paths, but you want to think about distributions. And actually, this, believe it or not, is one such distribution. Of course, it only refers to the electronic problem, and it's only stationary. I mean, quantum problems are already difficult enough in the stationary problem, but that is essentially what we're trying to do. We're trying to discover or to get good representations of ground or even excited state configurations of electrons. And so maybe Michele will one day come back to this problem. Okay, so what I want to say is that actually, in this field, there are 2 entirely different schools of thought as to how you should even go about trying to compute correlated electronic wave functions. One of them is what you might call quantum chemistry, and these are what you might call orbital-based correlation methods. And the idea in these orbital-based methods is that you first of all start off by solving for a mean field wave function. So you carefully optimize some orbitals, usually n of them, and so you have a bunch of occupied orbitals, then you have a bunch of virtual orbitals that are empty in the mean field state. And then what you start doing is you start exciting electrons from this ground state, single determinant form, into these into these excited state determinants, and then you entangle these excited state determinants with this mean field wave function. That way you generate correlation. So in quantum chemistry, correlation is essentially described as an entanglement phenomenon. And it took me a long time to realize that this is a crucial source of inefficiency in the method. Because entanglement is quintessentially a quantum phenomenon, but correlation is basically not really a quantum phenomenon. It's in fact largely a classical phenomenon. So correlation is just a statement that if you have two correlated variables, A and B, then the conditional probability of observing A given B is not the same as the probability of observing A irrespective of what B is doing. So correlation, you know, in classical probability theory and so on is everywhere, and there's nothing quantum mechanical about it. Of course, there are quantum aspects of correlation, for sure, and that's what makes the problem hard and challenging. But for the most part, one does not want to describe correlation from a pure entanglement perspective. And I believe one of the reasons why these methods are very expensive, and I highlight here this one in gold, CCST parenthesis T, it goes as the 7th power of the number of electrons, is precisely because it never really quite leaves this entanglement notion behind. Now, on the other hand, you have this school of thought, which is QMC, and this largely starts off, these are really concerned with real space description of electrons. So you have your n electrons, and they actually occupy positions in real space. And in that representation, these conditional probabilities are very easily expressed, because essentially it's saying that given an electron here, you want to exclude from its immediate vicinity other electrons. So this notion of correlation naturally arises in QMC, and they also work in continuum spaces, so you don't really have this basis set problem that I'll just mention. And they tend to be much more efficient, you see. The methods scale as power 3, power 4, something, but unfortunately with a very large prefactor. And then there's this nasty fermion sign problem, which means that one has to work with fixed node methods. And so in the end, although these are very conceptually beautiful methods, they turn out not to be really competitive with quantum chemistry when you want to do accurate calculation. And the methods which I've been trying to develop, which I'll talk about, really tries to combine these two. But let's first of all start off by looking at quantum chemistry and asking just how good are these methods, given that they're supposed to be the dog's bollocks, so to speak, of accuracy. How good are they actually? And so I asked my students, so we've been interested in looking at some weak non-covalent interactions. And so I asked my students, okay, take CCST parenthesis T and just compute the binding energy of the rare gas dimers. I mean, these are basically the simplest physical systems out there. Correlation is very simple. There is only 2 atoms. I mean, what could be simpler? The results were quite shocking for me. So there are 6 dimers. You know, you can take the homonuclear ones like helium, helium, neon, neon, argon, argon, or the mixed dimers. And what I show here is the error in percentage terms that you get in the equilibrium distance. And this is the more interesting one, is the error that you get in the interaction energy. So in the binding energy. So, for example, if you take this CCST parenthesis T in what's called an augmented triple zeta, this is not a small basis set, it's got about 100 functions, then you find that the neon dimer is underestimated in its binding by 40%. That's a crazy amount. And now I'm actually blessed with having access to very large computers, so I could push these calculations out. And so we went up to the next basis set, augmented quadruple zeta, and now the error for neon is reduced to merely 20%. I mean, there isn't enough computing resources to get us to this point, which is where we want to be. Now, just yesterday, I came across this article in the Financial Times. You see, 10th of September, the big read. Why is AI struggling to discover new drugs? A generation of startups have failed to live up to the hype. Well, no kidding. I mean, if for this simplest of systems, the most accurate methods could get to underestimate the van der Waals interaction energy by 20%, we have no hope, literally no hope, of designing a fancy drug molecule that will, bind to some cancer or something and unbind when it needs to, or doesn't bind in the right place, and so on. So of course, everyone can say, well, you know, you shouldn't do these naive calculations. Oh my God, you know, I did some straightforward calculations, not, you know, scaling things, etc. I mean, of course, I know I can do all of these, but if you really want to do just straightforward calculations and ask how closely can you describe physical reality, the answer is we've still got a way to go. Now, of course, we know that there are methods where you try to accelerate, for example, basis set convergence, and in quantum chemistry, they come under these terms F12. And so you can see that, yes, it does work. For example, here, you get the binding energy in this triple zeta basis set to now within about 5%. But I have bad news for you, because when you go to the next basis set up, instead of moving closer to this point, you move away from this point. So you don't even, with these methods, get the systematic convergence that you really should towards exactness. And then, so finally, these methods, which I'm going to be talking about, land us at these points. Still not perfect, but at least we're sort of heading in the right direction. Okay, so I mentioned I'm looking for methods that kind of build a bridge between these two worlds. And I'm firmly of the view that, you know, combining ideas is an essential ingredient to progress. That is, I think, very important. And a bridge to do this was actually provided by some very old ideas, essentially by Boys and Handy in the 1960s. But, I mean, they were just decades ahead of their time. They could not have possibly been able to do the kind of work that we can now routinely do with big computers and so on to investigate these methods. But the idea is that we can take correlation functions that come from variational Monte Carlo and feed it into a quantum chemistry technique by modifying the Hamiltonian. And that Hamiltonian, once it's informed by some correlation characteristics, can then be solved by any of these quantum chemistry techniques. And that leads to a dramatic acceleration, both in the basis set era, but also in the quality of the actual underlying many-body method. So the idea is as follows, is that, well, this is the equation we want to solve, and the idea is that we're going to factorize it into 2e to the tau, which I call roughly the classical correlation in the problem. Tau is going to be a real function, so this e to the tau is always positive. And then there's this phi, which basically contains all the fermionic characteristics that we will actually then compute using our methods. And if you now just plug this in and rearrange it, you end up with a new Hamiltonian that we call the transcorrelated Hamiltonian. Transcorrelation was a term that was introduced by Boys. I think it's a slightly unfortunate term, not least for various reasons. Nowadays, people have told me, you know, there are some countries in the world now that if you mention this word transcorrelation, you may even get your research discontinued, so it's slightly unfortunate. But it's actually nothing more than a similarity transformation. That's basically what it is, a similarity transformation. So it was an unnecessary term, but anyway, it seems to have stuck. And this now generates you what is, in principle, an infinite series. But if this tau only depends on the electronic positions and nothing else, then you can show that this infinite series rigorously truncates at the second order commutator. Okay, so it's not that bad, actually. Now, the point is the following, is that there are various things that we can do. One of them is that we can incorporate into this correlation factor cusp conditions, which are, so this is analytically encoded, and these cusp conditions then mean that this phi function is relatively smooth. So by incorporating cusp conditions, we can remove singularities from the Hamiltonian. And I want to mention two things here. What's known is that we can remove the short-range singularity, the fact that the Coulomb potential diverges at short distances. That's one thing. What is less known, is actually more interesting, is that we can also remove the long-range singularity, the long-range 1 over R12 tail, which is a major problem in achieving convergence of these wave function methods in solids. And I'll come back to that point. But these are universal features. But we can also incorporate more, let's say, system-specific features into the correlation function. So these are shell effects, long-range correlation, and so on, so that the terms in this transcorrelated Hamiltonian, the interaction terms, become weaker than those in the Hamiltonian. In other words, essentially what we're doing is we're arranging these commutators to have terms which largely cancel the 1 over R12 in the T is the electronic kinetic energy, absolutely. The potential energy terms commute with tau, and so they drop out, yeah. Okay, so the form of these correlation factors that we're going to be dealing with, this is shown here for a neon atom, and it's got various things. One is that it's got a cusp. So what you imagine here is that you put a nucleus at the origin, you put one electron somewhere, and then what I'm now doing is I'm dragging the second electron through the first electron in the direction of the nucleus. And of course, when the two electrons...
A very important person, and it was a pleasure to meet again Michele close to my hometown in Recco, where we had a very informal lunch with Focaccia di Recco. So tante
Informal but very good.
Informal but very good. So thank you, Michele, and thank you, auguri Michele, and thank you all for your attention.
So, any question?
Yeah, thanks, Daniele. Really, really cool. So just a curiosity, in the case of these M-xenes that you terminate with OH groups, is there any sort of spectroscopic evidence of these OH groups, and have you tried to, I don't know, compute vibrational spectra?
Yes.
And yeah.
This is the next step that we have, because this one is the new data that we have with a new material. And the problem is to have a setup where you have a surface that allows you to get the infrared spectra. This MXene is not like I thought that they are completely 2D and flat. They are flakes, and so, but yes, this is of course the
Other question? Well, let me ask you just something based on my ignorance of chemistry. And
okay.
In this carbon sequestration, you use this thing on the surface, but the typical methods are based on, for instance, amine molecules solvated in water, and you have to be able to absorb carbon and then to desorb and things like that. What would be the advantage of having the surface?
So, indeed, the point is that this surface.
You have
this surface, how I described here, had some kind of coverage, but we had, for example, no vacancies. So we plan to combine an engineering of the surface with some solvent, which would help to do the things that you are doing. So it's the combination of the two things on a material that is, on the one side, is two-dimensional, but is very robust, heavy, with 6 layers, and so it can really keep the CO2 in place.
Okay.
Is this the plan? Also
Okay,
for the next.
good luck.
Thank you. Okay.
Well, there are no other questions. I think we can move to the next speaker. Thanks, Daniele, again. Here.
Okay.
Does it work? Yes.
Okay, thank you.
Go ahead.
Yeah, is there? Okay, good afternoon, everybody. My boss is there, and today I'm really pleased to have a talk here, and I'm going to talk about in electronic structure calculations or computational Hamiltonian. Compared to previously talk and catalyst a few days, maybe this is more physical, at least I hope, okay? And this talk is, of course, is dedicated to the birthday of Mikene, so I must start with the connection with Mikene. So I used the Ponist, okay, the great Ponist Mao Zedong, Chairman Mao. Okay, everybody Chinese knows that, but maybe many foreigners knows that. They have a poem. Chairman Mao is a great politician, but also he's a Ponist. He wrote many. This is one. Okay, one line. So this exactly describes my story. Okay, my time. Almost 30 years ago, I was take a more than 80 days train then to the SDB, and then the DFT LDA on this blackboard by the talk of Paderewski, and then molecular dynamic simulation by Michele Pagnano. He gives this transparency here, okay, so on this screen. So 30 years passed, and 30 years passed. And during that visit, I became the first generation students who use Pagnano method. First generation students, I think, and that's not much senior, okay? During that few years, what I did, I wrote the two papers with Elio and Michele, one on this gallium. And these two papers, and one is on the solid, and one is on the liquid. I think the physics of these two papers is simple. So we discovered that this gallium could be a coincidence of carbon bond and the metallic bonds, both in the solid and the liquid. And I checked these citations, these two papers. So it's small, it's negligible compared to the total citation for Michele, but it's not zero. For more than 30 years, it does not die, okay? It's still something like 10 times a year. So I hope it will continue, okay? So this is my hope. But this is, I think, is not interesting work, but so after come back to China, because at that time, China have no computer. So I have to stop this kind of work, so I moved on other things. So since then, actually, I did not do too much of simulations. So 2 years ago, I get this invitation. I need to write something to this special issue. So I'm thinking, so I need to do something. So I come to remember the police gallium. I did not finish. During the work here, Elio asked me to do some solution for the gallium at high pressure. But at that time, I did not finish, and due to the various reasons. So maybe I think this is time to continue. Don't need to do the first principle Pagnano, but now we can use in this machine learning potentials. So okay, so I did it for the surface, for the liquid gallium surface. I want to look at, okay, so we know these bucket regions, there's dimer, or say carbon bonds. I want to see what's the properties of the real surface. invented some algorithms combined with the panorama, but the panorama cannot directly use to the paragonal system surface, so we need some special tricks to do this. And interesting to find that the first layer is metallic. Also, it's a simple liquid. I can say not catalytic metallic, but it's simple liquid. But apart from the first layer, it's very similar to the bark, as I think. So we figure out this kind of something like a phase diagram. It's not a phase diagram because what we wrote here is only structure parameters, not the physical properties. But anyhow, you can see the temperature and pressure, and the gallium have some really some interesting things. Okay, so this is for gallium. This is the story for almost 40 years ago. And then I say we can do this gallium surface, we can do the diamond. Diamond surface is more interesting. Under pressure, diamond is very special for the high pressure physics. And we do this diamond surface and see how it is stable under pressure. And we got it. This is a phase diagram. This is a really phase diagram. This is not a real phase diagram, but this is a phase diagram for the diamond under the pressure. Interesting is that at room temperature, up to something like 200 or 200 something, this surface becomes really unstable. So if this is right, I think it is something interesting to the high pressure people. So you cannot go to very high pressure with diamond. But this is thermodynamically. But kinetically may be different, okay? So, but this is the intrinsic properties of diamond surface and these high pressure or say constant pressure simulations. Okay, this is the two small work, and they contribute to the special issue of for the mechanic. Two papers are accepted, but I hope this could be appeared soon. Okay, let's come to this my talk about really talk physics of today. And nowadays, people talking about the machine learning potential. This is a breakthrough by Michele. But in the computational physics field, always need to solve these Combe equations. Okay, so when I was here in the CISA, always have some problems, convergence problems, self-consistent. Sometimes never get convergent, so it's really burden things. So actually, this self-consistent is not useful because you need only the Hamiltonian. You get the Hamiltonian, you have everything. But the self-consistent is just give you a Hamiltonian. So, and we know this kind of things cost a lot of computer time. And so we ask, is it possible to kill this self-consistence and using the machine learning is kind of neural network and give you these coordinates and then directly give the Hamiltonian. In this case, you save a lot of time, right? It's maybe at least 10 times or 100 times time. This is we did it, and this is it is successful. Actually, this idea is not the principle from my group, and it actually something like 8 years ago by I forgot the name. But they tried to do it for copper with some tiny binding Hamiltonians, okay, and then some people do it for molecules. And from Tsinghua University and Fudan University, we do say for the solid. And this is quite successful for some specific materials. You give coordinates and give you Hamiltonian. Okay, you never need this self-consistence. So today I'm asking, so is it possible to give you universal Hamiltonian for all the elements, for all the materials? Okay, so this is we have successfully did it. So what we did it. So we use in this materials project, everybody knows that. It's something like we use some 40,000 crystal structures or properties. And we build of this is a neural network. That's nothing new here, but you need to some tricks, not to some physical constraints to make it right, okay? And then we have developed some specific training process, at least basically two steps. One is to how to learn these Hamiltonian elements. And this, of course, you must input by the density function application calculations. And then we need to fit these eigenvalues okay, to non-eigenvalues. So essentially, we have these two steps, we really get it. And unfortunately, or fortunately, we are lucky to say this works. Works, I give some examples here, okay? So, for instance, this is, nowadays people are very much in physics, twist materials. This never been fitted to this learning data, input data. But you can see it gives the band structures. This, you cannot see the difference using your eyes. It's really up to mini electrons volts, 1 or 2 milli or even less. So this is by dot is DFT, and this 9 is by this machine learning Hamiltonians. So this really works, and so we can come to very complicated materials. Okay, this is very, very complicated. It's high entropy materials, and if you do DFT calculations, it's really time-consuming, and the students don't like it because the convergence is very slow. So use this machine learning, so we can do make this easier. So we did another test because we have these Hamiltonians. We can do anything. Okay. Maybe people know this is genome, okay? They produced, I don't know, 300,000 materials predicted. So we spend 1 day in our local machine and predicted these electrolytic charges, okay? And did all of the things. This is the statistics. This number of crystals and the band gap. You see this data set, almost the metals. And if this material is real, okay, so you can give you the whole world. What's the semiconductors with direct band gap or indirect gap? These ratios. I don't know if it means something or not, but this way we can give you some insight of this world, how the material is. Okay, so. Very recently, we get this Hamiltonian for version 2 with SOC Hamiltonians. Everybody knows that if you perform a Comsham calculations, you need SOC cost something like 10 times slower. And because of various physics reasons there, so we hope we can do it in your universal Hamiltonians. And to do this is a little bit tricky because SOC part is at almost 2 times order smaller compared to conventional this Hamiltonian. So we do it in a very tricky way. We first train in this Hamiltonian without SOC coupling, and then we add something 10,000 of SOC materials of these Hamiltonians and train it. First train this one and then train this one together, and then we get a very, very good results. Convergence is very, very good. So I give you one example how this works. So I say we have this genome, something like 30,000 or even more materials, and we're looking for, say, in this data set is any topological insulators. This is a physics intrinsic test, okay? So we start this 30,000, and then we do some searching, screening first. So say if these materials must have heavy elements, otherwise when SOC will not very big. And then it comes to something 100,000 of systems, and then we can calculate this band gap, and the band gap must be some regions. We take something like 0.03 electrons. You can choose any numbers, okay, but this is just the numbers. And then this could comes like 1,400, and then you can calculate this real topological invariance, say the Z2, and with this is only 1,000 something. You can do it very easily, and then we end up, say we have something like 100 something. these materials must be topological things. So these really enhance this kind of materials design or discovery. So, 10 or 15 years ago, to get one materials, you need to calculate something a few days. Now, this kind of things, if you repeat 2 days in my local computer, you can finish all of these kind of things. So this becomes much faster. So this is the Hamiltonians, but now I'm going to give you some applications, how this works. And so first is, electronic transport properties. This is the properties is hard to calculate. This kind of transport properties, essentially the key factor is electron photon coupling. Okay, so to calculate this one is not that easy because this LDA doesn't work well, and you need the high order function like Robert just mentioned, and also this DFPT does not give you the these phonons with high order functional. So this is a problem. So we had it before. For instance, let's say the gallium arsenide. This is the most well-known semiconductors. Even for this one, the people does not give you a right answer. That's because first you need to have this use high order functional to give this right band structure, and if you just use PPE, the mobility is much higher than experiment data, and also the breakdown electric field strength is smaller than experimental value. This is certainly is wrong. So we using based on this machine learning Hamiltonian, universal Hamiltonian, we can easily develop this new algorithm to calculate electron photon coupling. We don't need to do as previously. So with this kind of things, we can easily do this for gallium arsenide. So here you can see this is machine learned in the gallium arsenide band structure compared to conventional DFT. You can see. You cannot see the difference. So with this, you can calculate the mobility, and this is quite close with the experiment. So this is really the makes the materials calculations and feasible. So, and also give another example for this breakdown strengths. So this is important for the device people, not for physical people, but because they need to have a device is a very large breakdown strength. There is some theory in the literature or in the industry. So if your band gap is larger, your breakdown strength is larger. Okay, this is general pictures. Okay, so now we can calculate this now because we can do it using machine learning Hamiltonians. So we really calculate this can bring down the strength, but we find that this as this practice curvature does not have very clear relationship with band gap. So then we come to table to analyze it. Okay, so then what we found it. Instead of proportional to the band gap, it's proportional to the strange number, the maximum of tensor state. Maximum tensor state up to above this CBM, okay? So instead of proportional to the band gap, but proportional to the tensor state of the maximum tensor state. So then we calculated one, you can see this is really proportional to our formalisms. So this is a kind of discovery, so changing this well-accepted concept in the industry people for devices. So this example say we can now calculate these kind of things, and then you change the concept. Otherwise, if you're using conventional electron coupling theory to calculate this, you will never do this because that's too time consuming. So this is an example for this. Another example, so I say the carrier dynamics. Carrier dynamics is very important for the photo electrons, for photochemistry or photophysics. The physics here is simple. So you're using the photons, excited electrons from the VBM to the CBM, okay? And then see how this excited electron, the dynamics, okay? to do this is very time consuming because it's multi-scale problems, and there's many codes now in the society. But all of these codes are based on the first order calculations, and the limitation is very serious. It's come to 100 atoms or picosecond time scale. So this is because they need to do the electron photon couplings. Now using this machine learning, we based on this non-adiabatic hemodynamics, we use this spatial treatment based on this machine learning, and we can get this 10 times times faster than a conventional method. So you can go to very large systems, and also more physically. When people doing this kind of non-adiabatic MD, they always use this CPA. Now, this is classical path transformation, not the physics and CPA. And that means the trajectory of atoms always classical. Okay, always classical. Now, it does not depend on where electrons are. And then this previously people can only do this way. So now we use machine learning stuff. We can do it on the fly in non-adiabatic MD. That means the trajectory really depends on your electron, where electrons are. So we developed this kind of method, and then we can do the simulations. And now we are able to compare the previously using CPA. This is error bar, something like 100 milliliters per action. Now, but using our method, now we can say come to something like 1 order less, something like 7 MeV per action. So this is very efficient. So if we come to the power laws, previously if you were using conventional poor DFT calculation, it comes to n to 4. But using this machine learning is aim to 2. So this is much efficient. So this is open something like new windows for these kind of simulations. Okay, so I have another few minutes. I want to say what means universal. Why universal is important? I just, Zipan said, I think this provides the possibility to predict the materials with specific properties. Okay, everybody knows that we have something 100 elements, but materials, number of materials could be almost infinite. So how can you find the materials in this infinite space with specific properties? This is almost impossible. It was also impossible. So previously we give any atomic compositions, you give you chemical stoichiometry, you give structures, we can calculate properties. This is conventional physics doing this way. But if you're asking, say, give your properties, asking what's the chemical potential, atomic compositions, structures, and chemical stoichiometry, this is it was almost impossible. Now, based on this kind of machine learning or whole process, we developed this kind of trajectories or algorithms. We can do something. So we give examples. This is we discussed with Elio a long time ago, and we can ask these questions: What is a material with highest coercive energy? Okay, this now, can you answer me? So what is the material with the highest coercive energies? So if I'm asking you, say, elemental solid, elemental crystals, you can check a keto textbook, you can find it there. But for materials in the whole space, almost impossible, okay? So we tried this for a long time, but now we give some partially solve these problems, these simple problems. So we are looking at these ternary compounds, not for 1,400 of ternary compounds, and this XYZ can be smaller than 6. This possibility is something like 100 billion. So that's almost if you do it one by one, that's almost impossible, but we can do it tricky with these universal things. So all this kind of potential is based on the DFT. So we know that these elements with F electrons, we cannot do it good. So we just select the 42 elements with this blue. So I'm quite confident that this PBE or something works reasonably good. So with these 42 elements, we construct the universal potential, and using this universal potential, we find something interesting. So the final results that is, remember, we started with ternary, but the final result is zirconium carbon. Zirconium carbon is the highest coherent energy materials. Of course, diamond. Everybody knows diamond. Diamond is here. Diamond is next to. So we started with ternary, but in the end, it's come to diamond and zirconium carbon. So this is a way to answer a question, but this way we don't include F electrons elements. Okay. So with this, we can do more things. So we asking, what is the highest Bach modulus? What is material with the highest Bach modulus? The answer is diamond. We did not find any materials. Bach modulus is higher than the diamond. But anyhow, so this will show the method how to do it. The last applications for this universal potential is we need to design materials. And I don't have much time. So, but you know, for the microelectronics, the miniaturization of CMOS get some trouble. So trouble is a sub-threshold string integrations. If you don't understand this, that's okay. That's because when you chips get smaller, you need more energy to make it on or off. Okay, so people propose that say you use cold source transistors. What means cold source transistors? That means you need materials with this kind of denser state. That means up to some energies, you have a minimum here. Okay, this is the people proposed. This really works. They design this kind of real symbols here. It works, but now it works, but it can be industry applied because they use many different materials. It's incompatible with the silicon. So we try to use silicon design these silicon nanowires. We train in the silicon nanowires, Hamiltonians, and doing some designs. We really find the 1 nanowires with this kind of band gap here. This is band gap. Okay, real band gap CBM, VBM, CBM. Okay, we have something, a pseudo gap here. This pseudo gap is exactly what the industry people needed. So we've designed it and make a test, and it really works. Okay, I need to skip it. But anyhow, now we have all these kind of things using website. Elio, you can do electronic calculation now because you just open your mouse. I need the band structure of silicon and then give it. You need the band structure of what? Even this material does not exist, they'll give it. So this combined with this large language model and give you all of this kind of electronics properties. So you don't need to teach me using carbon anode, but now we can do it automatically. So this is the work with our people, a few professors in Fudan, Hongjun, Jihui, and Cui Weibin Xiu. And in the end, I say we are going to have a celebration of CPMD, Capilano MD 40 years in China. We have this international symposium in Fudan from October in Shanghai. We are all welcome to join. Okay, so the last transparency. So this is the picture with Michaela. This is Michaela with quantum energy workshop, and Roberto was also there. This is you remember where it is? It's in the house of my Chinese supervisor. She is a rich person with a garden now in China, Suzhou, Wang Siyuan. Okay, in Chinese people know that, and this city there. And this is very feel proud of it. This is last year, and this is Chinese know that this is China mostly important meeting places, Congress Hall, something like that. And Michaela was selected as a foreign member of Chinese Sciences and have meetings. I was there. Unfortunately, at that time, I'm not in right shape. A doctor asked me to stay because I have an operation.
I know you may take great effort to greet me.
Yeah. At that time I say, okay, but I really feel glad. So last, happy birthday, Michele. Okay. Thank you.
So, question? Yes.
I might have missed this detail. For your code sham, the machine learned code sham, is that specific to the basis set? So, like, do you have to train a new model if you increase the cutoff?
Yes, I will use local, atomic, atomic basis.
Then I have a question related to that. How far do you have to include interaction between atoms?
But this is just local basis, like visual open omics. We have a cutoff, something like 5 or something like this, yeah.
And do you, so you have a Hamiltonian that is sparse in some sense because
yes.
you do not have, and do you use this sparsity to diagonalize or not?
Not yet. Not yet. Yeah.
Okay.
Yeah.
And perhaps, just one more question. But there are more from, yes, go ahead. Well, I can ask.
This is a very professional question. And we tried that where if defects is no charge, is neutral, there's no problems. This is exactly like Roberto asked. If there's no long-range reductions, is no problems. So because we learn something, you can. But if
No, you come over here.
Okay, if the charge is different is charged, some problems we need to solve. This is also for the machine learning potential. Also, yeah.
So I have a question also related to that. In the old days, we were doing liquid silicon and metallic amorphous silicon, so disorder structure, and we could compute the density of state and look at the band gap or these other things. So have you used your universal Hamiltonian also for some of this disorder structure, and how well does it work?
We do it for silicon oxide.
Yes?
It's no problem. But the no problem is if you don't have this special vacancy or something, it's charged. Okay. Mm-hmm. Yeah. This works well. Yeah.
Okay. Thank you. And thank you so much. Put it over here.
Perfect.
Well, okay.
It looks good. You can.
Okay, yes,
yeah, all
it
right.
works. So
all right.
I think you are the last speaker of the section, and unfortunately I cannot read what is over there, but I can read from
there.
your screen. So Chris Mundy, he will, from the Pacific Northwest Laboratory, he will tell us about beyond the Debye-Huckel limit towards a general theoretical framework for concentrated electrolyte.
Thank you, Roberto. And I want to first thank the organizers, Ali, for inviting me to this wonderful conference. Can you see my pointer on the screen? Just making sure. Okay, and of course, the next slide, I just want to echo all of the sentiments that have been stated before. I'm very fortunate for this kid from Montana, from humble roots, to be part of this great community. I was a postdoc with Michele from 1998 to 2000. It changed my life in many ways. Great mentorship, and it introduced me to this great community where I enjoy lifelong friends. In addition to catalyze my personal life, I have a family now, 25 years of marriage to Marion, so thank you. And this picture was sent to me. I didn't take this. This is what's interesting. It was sent to me by a student that was at the Pitzer Center and recognized it. So this is around 1999 when David Chandler came to visit. And again, this is just testimony that Michele makes us all feel welcome and part of this nice community. So happy birthday, Michele. And I'll move on to science. So I'm going to talk to you a little bit about something different, screening and concentrated electrolytes and the importance of this. So we're all taught in school that the more salt you add to a medium, the screening length goes down. And that's sort of, you can see that in this sort of classic electrolyte theory. So this means that if you have charged objects in solution, you add more salt, screening goes down, these things can get closer. So what is it about reversible screening or the reverse of this, and does it happen, is it irrelevant? And the idea is that although under screening, so where the screening length at some concentration goes up, it seems rather counterintuitive. This has been known by Kirkwood since in 1936, okay? So about 10 years ago, we're waiting for the community for some sort of measurement of this, right? This is a very interesting theoretical construct, I'll talk about it, but the measurement has still had not been performed. At least I didn't know about it. And Sue Perkin at Oxford presented sort of these results that I'm showing you here in schematic. So the idea here is that she very carefully labels this the decay length, but the idea is that she has two mica sheets, and she looks at the disjoining force as a function of concentration. And you can see that it's sort of what you imagine is you sort of dumping at low concentration, the disjoining force sort of is not screened, and as you add more electrolyte, it screens up to some critical concentration, and this is going to be around a molar. It's not something crazy. And then you get this reversal, okay? Her measurements are still being interpreted. Importantly, I said she labeled the y-axis as the decay length, but it has widely been interpreted as a screening length. The upshot is at low concentration, the forces between plates are screened in accordance with Debye-Huckel theory. That's what she measured at a critical concentration. It reverses, and understanding this under screening is sort of the goal of, and relating it to things that we know of ion correlation. And we've seen a lot of talks on nucleation of materials, et cetera, here. So all of this is dependent on ion-ion correlations and them conspiring to do really interesting things. And thus the understanding the concentration dependence of ionic correlations can impact many important areas of research, and what interests me is the fundamental understanding of how we probe this and understand it, and here's some references for the interested person. So again, to sort of show you that where we are as, you know, in terms of just how complex these systems are, everybody wants to understand diffusion constants, viscosity, and presence of concentrated electrolytes, and this is something the battery community really wants to know, so it's very important. But right now we're sort of stuck with empiricism. And this is sort of the famous, this is the Jones-Dole equation. It relates to the viscosity to the concentration, right? A square root of a concentration, a coefficient, and a linear in concentration with the B coefficient. And it turns out that these B coefficient is related to the classification of the sort of intrinsic ion, whether it has strong hydration or not, and this has been studied by a lot of people, even your Princeton colleague, Panagiotopoulos, spent a lot of time on this, including us, and the A coefficient is the one that's more related to the collective, or the charge-charge correlation. So in order to understand diffusion, or some sort of transport quality, you have to know something about the local structure and something about the collective. That makes sort of sense. And so in my previous, let's say, years, we focused on studying sort of this B coefficient at PNL because it's based on the intrinsic or solvation of an ion, and we can do very exquisite measurements with XAFs, providing a body of work on molecular level picture of solvation to, structure of solvation to free energetics. Now I'm going to turn to the left-hand side, or I guess, yes, it's my right, your left, and trying to understand the collective effects and using X-rays. Now, we've learned a lot about X-rays at this meeting, and they've been using the sort of the large Q to use as an order parameter. But I'm going to be focusing on this very low kind of pre-peak region, right? This is sort of the collective effects as Q goes to 0, to sort of, and try to convince you that we can understand things about screening and measurement there. Okay, so first we're going to establish some notation in this lecture. This is sort of quick. There's be a little bit of liquid state theory here, but we'll go through this quick. So I'm going to be talking about H of R's. These are basically G of R minus 1, nothing fancy. And of course, there's going to be Fourier transforms that go from H of R to H of Q. So this is the most important stuff. So there are these things called structure factors, S of X of Q, which are sort of weighted by atomic number and concentration of the correlation function. So atomic number is necessary. The higher the atomic number, the more scattering you get. That's why they like to do high Z metals or high Z ions, okay? This is the experimental signal, okay? Now, you can also find other sort of combinations. There's ones that are based on density-density correlations, or they're simply concentrated, weighted, again, linear, because and they're sums because concentrations are positive. So to understand charge correlations in screening, you need another appropriately weighted structure factor, which is called SZZ. And as you can see here, it's weighted by the charge. So this is going to be a strict sum, but it's going to have plus, plus, minus signs, and all of that. And if you continue reading Hansen McDonald, that if you know SZZ, you have direct access to electrostatic screening. Okay, this gives you the direct access to electrostatic screening, but is not directly measurable, and that's the trick. So we want to get screening lengths out of measurement, but it's not directly measurable, so guess what? You're going to need theory, right, to help us understand this, okay? And so the necessary ingredient, as I showed you, is that requires radial distribution functions, not so hard. But thus we're going to need some sort of a sampling method. And of course, there's MD, Monte Carlo, and I'm going to show you that we're going to be doing something in the vein of sort of liquid state with the Ornstein-Zernike equation. And I'll tell you why we're going to need this, but this is sort of the equation, which is sort of a convolution between a direct correlation function, which is related to the potential, and you can get out a converged pair correlations. So we'll talk more about that later. So again, let's just go back to feeling comfortable about it's 101 years since Debye-Huckel. The goal is to go beyond Debye-Huckel. And this is one of my favorite slides. Because the beauty of this for the dilute limit is that we have charges, okay? And they're not even getting close enough to know they're hard cores. They're just floating around in solution. You have a long range interaction, Coulomb, 1 over R. But the correlations are short range. The H of R's, you can see, sort of decay quickly. That's profound. At least it's really affected me in terms of understanding this. There's something many-body going on that brings in these screening lengths. Now, it turns out, to complicate things, to go to higher concentration, all you have to do when you go to higher concentration, you just have to add what we call frustration, which is just a short-range hard sphere core so they don't overlap. Okay, and that's what happens. So I made these things now hard cores, and it turns out once you do that, you find that the correlations, they still decay, but they can decay in an oscillatory way and with a particular Q naught or distance, and that gives rise to some complexity, okay? And this has already been known by Kirkwood, and it gives, and of course, the whole idea is that, this is all based on just simple concepts of adding simple frustration to the system. So as I told you before, we're really, maybe this lecture could be over if I could just compute all these G of R's in the right linear combinations and be done with it. And we're all, we all spent our lives looking at these and computing these. And G of R's are very nice, and we're usually worried about the wiggles in the short range. But it turns out to get screening, you have to go way out here, okay? And I'll tell you, you have to get even further than 20 angstroms. So this is sort of, it's the asymptotics of the G of R. And in order to access this, we're going to need something more than just MD simulations of any form, because it's hard to get those converged, especially if you wanted to do ab initio. So I have to present to you a reduced way that we will get at these and hopefully get at screening and compare to experiment. And so we're forced to consult theory again, but unfortunately we only are bounded by simple theories when we're trying to understand screening. And I'm going to give you, again, the left side is dilute and the right side is concentrated. So for the students, I think it is worthwhile looking at these derivations of Debye-Huckel theory using the linear response and the thermodynamic route, what I'm showing you here. This is now, what we call them are Chandler's white notes. I think Chris Delago knows about these, the existence of these notes. And I think David Limmer has retyped them up and put them into his book, so you can learn it from it there. And this is a very informative route. So an idea is there is I showed you that Ornstein-Zernike equation before, but all I've done now is I played the trick where I replaced the direct correlation function with the potential, which is 1 over r. I can take Fourier transforms of 1 over r to get 1 over q squared, and I can then solve directly for hzz of q, and you get this nice Lorentzian, okay? That's a Lorentzian, and if you look at the poles of the Lorentzian, you go to the real space, you get the celebrated Debye-Huckel. So the poles of this Lorentzian here with q, that'll come up a lot, give you this nice damped exponential. Now for concentrated systems, there's no simple theory, but we can conceptually, as I told you, introduce the concept of frustration in many ways, and I'll just start here with simple concepts of frustration we can do on a lattice, okay? So if you look at the simple nearest neighbor Ising model, we're just gonna have charges interacting. You can have a J term which wants these two charges to be aligned. That's plus plus, it's short, right? Short. And then I can put the Coulomb term, and this is augmented. And this will want them to be plus minus, okay? So now you have a frustration between plus plus and plus minus. And if you work through the mean field theory and you turn the crank, you find out that you get a structure factor, or hz of q, that looks a little bit different. It doesn't look Lorentzian, it's non-Lorentzian. And it turns out if you Fourier transfer this, you get these celebrated damped exponentials, okay? So the important concept is that the poles of SZZ or SZZ and HZZ of Q give us the screening lengths for the dilute, and in the dilute limit, the Lorentzian is established. For the concentrated case, the open question is what is the exact form of this denominator to give you sort of and whether we need a more simple model than what I just presented here to understand concentrated electrolytes. Oops, went long way. Here we go. So to give you a feel for how these things look in the dilute limit, again, if you take, again, the left-hand side is the dilute limit. I showed you these are the Debye forms. So if you multiply HZZ by R, right, and then you put it on a log scale, you see that you will get to a point where it's nice, this linear, and this slope will be the Debye length. Okay, but look how far you have to go. You have to go 15, 20 angstroms in order to see these sort of correlations out there. And if you go to the finite concentration, I can plot out these things, and you see that you get, again, you get the envelope, which is a screening length, and you get sort of this introduction of this other length scale, which is Q0, which gives rise to these beats. So you can see all of these things if you get G of R's that go long enough out. So this was also established by J. Rasaya in the 1970s. He did some of these calculations, okay. And again, now we go back to sort of putting these pieces together, so understanding what they call the Kirkwood line and the relationship to what Sue Perkins was talking about. So I will call this form up here, this is the so-called the Tubner-Stray form. All we need are the poles to construct the, quote, phase diagrams of sorts that separates low concentration Debye-Huckel limit from the concentrated regime where there are two length scales. So the way you should look here is that at low concentrations, you follow this form will give you sort of the Debye limit, right? You can see K Debye and A0 are very well overlapped, and then you'll get a little bit of deviation from Debye-Huckel, which is nice, but look at these concentrations. They're very, very low. And then all of a sudden you hit this cusp where then it reverses length, okay? And then you build in this other length scale Q0. And this is this place where you build in this length scale, and the top is called the Kirkwood line, known in 1936. And this is essentially the inverse of what I showed you with Sue Perkins, because I'm looking at inverse lengths. So you could ask the question, why don't we classify electrolytes in terms of A0 and Q0 instead of kappa? That would be something very interesting. Excuse me. Okay, I'm fine. So the way that I like to look at this is that an isotropic fluid, I'm just going to play this as the only movie I have, so I apologize, or maybe it doesn't play. How do I get this thing to play? Is it playing? Uh-oh. Well, it wouldn't be that interesting anyways, because it'll be just a bunch of things wiggling around as a fluid. But the way that I think of these fluids is that these things are, it's an isotropic fluid, and there are these sort of fluctuations that are low energy, low free energy, okay? And I learned about these in my PhD thesis studying complex fluids, and it's these low, these low excitations, these sinusoidal soft modes that give rise at a particular Q to the sort of emergent structure sort of phase, okay? And that's how I like to view these complex fluids. Oh, in play, there you go. So you have this thing moving around, not much interesting, but underneath there, these low energy fluctuations, okay? So let's get to the experimental results. Okay, so this is really sort of the beautiful thing because our colleagues go to the light sources, and so let's look at strontium chloride and erbium chloride, and you can see these are the straight S of X experimental measurements, and you can see that the evolution from a Lorentzian over here to this sort of non-Lorentzian form over concentration, and it happens for erbium chloride, and so we can fit this to the Tubner-Stray form, and you get this nice sort of A naught goes up and down. So we're fitting these decay lengths, and we're seeing this change in sort of screening length. And we're building in this other length scale Q naught. And again, check out these concentrations of where this happens. This is extremely low. Okay, so now, in order to, so one of the problems is very low concentrations we don't observe in experimentally these sort of Lorentzians, and that's a little bit of a stickler. But for now, and I'll reconcile this in the next slides, but for now, just accept that we have worked hard to establish, because we have to establish that S of X and SZZ are proxies for one another, and we did it, and that would take another 20 minutes to talk about in this lecture, but we did this in this paper that's cited. I'll get back to a little bit of the highlights, but all I need to prove to you is that I can reproduce the line shape of SX using only the ion-ion correlations. If I can show you that I can get SX from only the ion-ion correlations, then I can get any linear combination I want and get to screening, okay? And that's a very powerful concept. And the details will be found in our recent paper here, but right now we'll just proceed with caution. And so I just want to let you know that this isn't some fantasy that I'm making up about these low excitations, because if you look at things like calcium chloride, it forms a hydrated phase, right? You can hydrated solid phase. So if you plot the Q naught as a function of concentration, you see that we didn't go to low enough concentrations here, but you can get Q naught plotted on this scale, and it goes up to this point here, and this little star is going to be the Bragg peak Q naught of the emergent solid phase. So these fluctuations that are occurring in the liquid are there, and we want to probe them, and they're related, and they're isotropic. That's what's interesting to the solid phase. So how do we probe this with theory? It's a very simple idea. We call it a molecular informed hypernetted chain approach, okay, MNHC. So we treat water at the mean field level. So as alluded to before, we need a reduced model to sample low concentrations in the long length scales. So we construct the model simply by using the intrinsic potential of mean force. So I take two ions, I put them in a box of water, I construct the potential of mean force. That's what I show here. Okay, and then I just assume that they interact through epsilon, which is a dielectric, and this is the potential. I have a short range that is determined molecularly, and then what I do is I know I'm doing a Coulomb system, so I spit on the end and I attach the 1 over R. I have my potential, okay? And then I can use the machinery of the hypernetted chain closer and this Ornstein-Zernike, and I can go to work, okay? And get all the interesting stuff, okay? And just to show you, it works remarkably well. So the molecular hypernetted chains well to all atom molecular dynamics where I can actually do the comparisons. And so you can see SZZ of Q with all atom versus the molecular hypernetted chain, and the results are pretty remarkable. And you can show why we need this, because if you go down here at high concentrations, you can do the simulations, and I show you that 3 molar, right, between the all atom and MNHC, that they overlap very nicely in this sort of asymptotic limit, a little bit of deviation as you would expect in the short range, but you can actually get very nice converged A naughts and Q naughts. And I can go down to 2 millimolar, and I can get perfect Debye length. So those correspond to Debye-Huckel theory, okay? This is very nice. And now this is sort of to show you that we do know what we're doing, and this is sort of a nice sort of, I would argue, exclamation point on what we did, because I have to sort of understand these low concentration scattering experiments that don't have these Lorentzian forms. And it turns out that the reason that we're getting these funny humps and bumps is that I told you it has to be pure ion-ion without water being a mean field. But at low concentrations, it turns out that the water is, forming these hydration cells, right, around the ions, and those are contributing to the scattering signals because there's so little of the ions in there. And when you add this through a form factor, you can see with our modified hyperneted chain plus a modified form factor to take account on this hydrated waters, you get the line shapes are beautiful. So now I can actually use our theory to compute screening lengths with the proper linear combinations to compare to experiment. And here's sort of the results, the really beautiful results. And I'll just stick to the ones, the last two. So now for strontium chloride and erbium chloride, we have actually a Kirkwood diagram, right? And you can see that turns out that the Q naught it's very different than I showed you before, because now Q naught, or Q, excuse me, the other length scale doesn't start to occur when you can see that when we start to change the slope of the screening length, but it actually is sort of there at very, very low concentrations. So we were very intrigued by this because it doesn't fit the classic picture, which is up here. So we started to call these generalized Kirkwood transitions. But then the question is it because we have crappy data and we're doing crappy simulations, or are these things actually real and there's something fundamental about divalent and trivalent electrolytes producing a very interesting screening phase diagram? So we need theory. So the extension to Weiheckel theory, as I said, are very difficult. But if you go back to the work of Michael Fisher, he starts off with this very intriguing form. He essentially uses this concept of soft modes, and he basically imposes these soft modes to break the symmetry and asks what the response is, and he has a direct route to the structure factor, and you get this beautiful form in gray. Now, if you look at this, what you find is that you have something that looks sort of Lorentzian right here, right, plus some gobbledygook on the end, that contains all of the correlations. So when G0, when this term here is 0, you have the pure Weiheckel limit. When it's not, you have all your correlations. So that contains all the correlations. So this is the new picture that we have. I have, what 5 minutes left, Roberto? 5 minutes, okay.
Including questions.
That's fine. I can do it. Okay. And so I'll just sort of quickly go through this. So in the intrinsic picture, we know that ions interact, 1 over Q squared. And again, you go to Hansen-McDonald, and again, once you know SEZ, you have essentially the interaction of the electrolyte. In this sort of low concentration, we know, again, we know the form of this chi of Q when you read Weiheckel, Hansen-McDonald, it has what they call the epsilon of Weiheckel Q, which gives you this sort of nice Lorentzian. So we postulate a form based on Lee-Fisher that this is the general form. You have basically the Weiheckel term, plus we're going to stick all the sins of correlation in this sigma of Q. And if we have a theory for sigma of Q, then we have a theory for correlation. And so the first thing I'm going to tell you is that we can extract sigma Q from simulations, okay? And just to get an idea of what this thing looks like, I can just plot the Q space and extract it. And you can see that for simple hard sphere models that have been in the literature, you can see that this correlation term kind of goes down and wiggles out and dies off. And this is the Tubner-Stray form, which seems to be the one that I showed you before, so that's not general enough, okay? So this suggests that these things don't follow some simple power series in Q, right? There's some more complicated structure to it. So how do we understand that? And if you go actually look at the molecular dynamics version of these with different interaction potentials, you see very stark differences between quantum PMFs versus classical in terms of the form of the correlation. I think that's fascinating. But this is the last couple of minutes. So we construct this theory. So now imagine a big system where you have charge density in these voxels, okay? So I can look at the charge, or I can look at the mass. And so we know how the charges interact. They interact as 1 over Q squared. And I know how the masses interact, because this is what we learned from derived Ising models. They interact in this nice power series of Q. And then we're going to take inspiration of the literature about how the N and the Z interact. And we construct this really nice, simple Gaussian theory. And we use an ansatz. So this is how they interact. You can see this is the Coulomb term, and we add a short-range piece to it. And then we have these other pieces which we construct based on simply the short-range part of the direct correlation function. So now I can get those from the hyperneted chain calculation, plug them in, and actually see how it works. And it turns out that it works beautifully. So the take-home message here is that sigma Q, as I told you before, it looks almost like a ratio polynomial, so it's not just some simple polynomial. I can actually get the liquid state theory predictions perfectly on it, even when they're... Exactly, you said it. It's a Padé approximate. That's exactly what we use. And we show that in the symmetric case, it turns out in our theory, the cross terms go to 0 as they should. In the non-symmetric case, we get these beautiful terms in a quantitative agreement. And so here's the upshot. Last slide. The take-home message. Classic Kirkwood lines break down for multivalent electrons confirmed by simulation, theory, and experiment. So we now have access to measuring screening lengths by looking at the asymptotes of S of x. The pre-peak region encodes all of this stuff, and that's beautiful. So you have to go way down towards the Q equals 0 limit. These provide really true electrostatic screening lengths. And if you go and you use our theory, you can see that we get these very funny looking sort of generalized Kirkwood transitions for, that the second length scale doesn't appear when it starts to switch sign. This comes out of your theory. So you need this coupling between mass and density. And I think that's very illuminating. And we've provided a very simple Gaussian theory to provide this conceptual picture that we can actually check using simulation. Underscreening is observed. Wow, that's neat. It's not anomalous, the one that Sue Perkins, but that's another day and another talk. And I would like to just stop now and thank you for your attention.
Thank you. Question.
Thanks, Chris. Fascinating work.
Thank you.
Two short questions.
Yeah.
One is, so you touched a little bit on the role of coordination of water and solvation shells. And I was wondering if this extension of the theory can be further extended to non-aqueous solvents. And the second question is, so here you look at sort of basically spherically
symmetric ions, yes.
Symmetric ions.
Right.
So how does that work for non-symmetric ions, which often are used, for instance, in concentrated batteries nowadays?
Those are great questions. So the first question is, yes, you can extend these things. You just need to know the dielectric constant, and you can play these games. The second question is much more difficult because, as you know, there's no simple sort of integral equation protocols for molecular fluids that will work quickly and easily. And so we're sort of bound right now, and we're stuck there. We can do the simulations, we can treat those things as spherical particles with the PMFs, but we're missing sort of these internal degrees of freedom. In fact, we have measurements being done on nitrates and things like this, and it turns out that to this point, it's getting us quite a bit of the way there, but it's not as quantitative at this point as the spherical ions from the scattering. Thank you. I think you have to turn on your microphone, or I can't hear you. I am not the Mikhail Sprick whisperer. I need to hear him. Okay, just scream, just scream. All right, I'll listen carefully.
Very, very nice. But in the last minute, you just took not explain the.
Yeah, okay, so I will be dangerous for you. So I've talked to Sue Perkin and I've learned about things. So I think right now that if you go to her sodium chloride results with the plates, right, there's no question that when she reverses screening, her reverse screening lengths are much larger than ours. And of course, what's scary when you go to the ones in the Debye-Huckel limit, from her point of view, they just follow Debye-Huckel theory. But if you look closely at her data, she only has a couple points in that low dilute. Okay, so what's your question? Better.
The problem is, can you extend this to the input?
Yes, we can, and that's the trick. Yes, these concepts work for inhomogeneous, but not in the sophisticated mica. But I can put a hard wall. I can look at ions within sort of a. Exactly. And we still don't, and I think that's the key to this whole thing. You need, in my opinion, she was saying in her earlier work, possibly tacitly, that these measurements corresponded to bulk properties of the electrolyte. But I think the role of the interface is going to be a crucial. Yes, so there you go. So there's a lot more work to do, and it's a lot of fun. Oh. Yes. Yes.
And then they use these.
Exactly.
How does your stuff
map to that? So the dream was, I thought that we were smart enough that once we wrote this theory that we could then derive a free energy functional, so to speak, and go back and actually compute activities. And what I would love to see, the dream of mine would be, because activity coefficients have these funny curves too. It'd be fun to relate to where these things swap up to where these screening lengths change. But the problem is that is harder than I expected, and so we're still struggling with this. And I've consulted Jan Levin, who knows these things very well. He told me to give up. But from Michele's, I will not give up, and I will keep banging my head on this wall till I get through it. Because I think but it's a great question. It's a hard problem, at least for me. Kirkwood-Buff integral, yes. Right.
very well in that value?
You still need the G of R's for Kirkwood-Buff. And you have to do the integrals, right? So that you still have the same kind of problem. They always have to patch up the tails. That's the problem with Kirkwood-Buff, right? You never get a nothing for nothing here, right? Kirkwood-Buff, you do the integrals over the G of R, but they have to go to infinity, and it's really hard to get those things to, you need doing it with, you talk to the experts who do this, they have tricks of patching these things up. I like this sort of liquid state approach, but maybe it's a little old school. I'd like to modernize it.
Question, we can thank the speaker.
Thank you.